non-smooth response. Okay? So what's been done? There is recent work. It's very recent. So this is in the context of disease, not in the context of predator-prey. Predator-prey, this stuff has been done 20 years ago. In the context of disease, to the best of my knowledge, are the recent results of Force Team in Arizona. Farrell is his former PhD student, now I think a postdoc, also at Arizona, who show various things. So let's talk a little bit about disease now, all right? Perhaps, in the theme of the session, and as I promised, I will talk a little bit. Again, I'm no expert. I don't really work on disease, but I did, a few things, and I think it's interesting if you think of these sorts of models. So you've probably seen lots of SIR, SIER, and all of these models. You can have a population which is susceptible. Typically, everyone's susceptible to a disease. People get infected, and then when they get infected, various things can happen. You might recover, you might die, you might be latent, all kinds of things. I am going to consider a subclass of these models called SI, susceptible, infected. So X1 is a class of the population which is susceptible to a certain disease, and people can leave the susceptible class and become infected. X2 is those people who become infected. I'm not concerned with what happens after infection. Anything can happen as far as I'm concerned. Some of these persons may die, for example, COVID, underlying conditions, age factors, healthcare issues, insufficient healthcare issues, whatever. Or they might recover. Or they might not even know that they had the disease, all right? But I'm not considered in breaking the X2 into various things. So the way I'm going to model this, or the way Team and others model this, is if there's no disease, right, if X2 is not there, then the susceptible population essentially is logistically controlled and grows to a carrying capacity. Okay? Now, because of the disease or the infection, you will lose people from X1 at some rate, at some incident rate, F of X1, X2, into the class of infected people. And then, dying or recovering or whatever, going out of infected. This is not important here. Now, what does F look like? So if you look at the disease modeling literature, it is huge literature. F can look like many things, and people try to fit it to various data and things. Team et al. Looked at a series of virus infections in salamander, right? So it's an amphibian group, where the best fit is a non-smooth response. So the way the salamanders are moving from susceptible to infected is at some rate X1, X2, this direct product, but the P and Q are both less than 1, so it is a non-smooth. Okay? So what is Team's result saying? So I'm not drawing the null lines and things. I'm looking at just X1 and X2. I'm looking at the stable manifold of, right, the origin. And what Team's result is saying is there is this curve in the phase space, some function of X1, such that initially, if the infections are above this curve, right, you will go extinct in finite time, right? Everyone will get infected in finite time. You'll hit this axis. Once you're infected, right, then you will be pulled down here, essentially in infinite time, okay? There's a huge gap between what he can prove and what actually happens, right? As long as you are theoretically above this stable manifold, the same thing will happen. They can't prove this, of course. For them, they need initial condition above this. There's this huge gap here. Okay, so we can improve this a little bit. You don't need so many initial infections, right? You can actually have less and still go to the infected class in finite time. And then, whatever happens from there. So some results of ours are that you don't need infections higher than G2. So G2 is the curve from Team et al. The purple one is recent improvement. So the solution X1 will go extinct in finite time for initial conditions, right, between, say, 1 and carrying capacity, and for X2 more than G1. So there's lots of data here where you can, rigorously prove that you will, still get infected in finite time, and once you're infected, you will go down here. Now, something of interest to me then was the business of, quarantine and protecting. I mean, at the end of the day, how do you prevent this? So the claim is you quarantine, right? So you protect people who are susceptible. It's also, how do you do that? So in the predator-prey literature, you can also protect prey, right? You can protect those who are susceptible by giving them something called refuge. A refuge is a protection zone for prey, right, where the predator can't attack it, which is something I've also worked on quite a bit in the past. So the classical, there's lots of models of refuge, right? So you can have a spatially explicit model where you actually have zones where you protect. There could be multiple zones, or you protect only a of the prey. And this is a more classic one. This R is, the fraction of the prey, of the susceptibles here, right? If R is 1, then no one is protected. If R is 0, everyone is protected somehow. Everyone is absolutely forced to quarantine, live in their quarters without any kind of social contact, if such a world were possible. Of course, there's going to be contact, right? But in an ideal world. So the result says that there exists a refuge, which depends on initial data and parameters, and an interval such that for any refuge more than that, and certain susceptible initial condition range, that X1 does not go extinct in finite time. In particular, X1 persists for all time. So you will not get infected if I can protect, right, enough people. And there's geometric ideas in the proof, but essentially it goes back to these pictures here, right? By changing R, you can lift or drop these manifolds, okay? And so if there was data that was going extinct, right, say data here, by manipulating R, you can lift the blue above that data. This blue line will go, and so that data point is now below. So now it's below the stable manifold, right? So it will not go there. It will go to either the interior state, or maybe there's a cycle or whatever. But that's the geometric idea. So refuge can help, right? Quarantine can help. To what extent it can, of course, that's a managerial thing, right? Because you tell people to quarantine, that doesn't mean they will. So it depends how you enforce these things in practice, and this can change depending on local policy, government policy, social, and things of that nature. But I think I'm sort of about at an R, so I'll probably end here with just a few words of sort of current experiments that we are trying. I showed you all of this modeling. And with Susan Bailey, who's an evolutionary biologist, we're actually trying to do some of these things in the lab. So you can think of bacteria as a pest or an invasive species, and you might think of protist as a predator that eats it. And these experiments are sort of easy because they're all done on a agar plate, and you have electron microscope techniques to count bacteria, and then you put in protist and count numbers. So we are able to grow them together at this point. The additional food is has not come in. We're still thinking of sort of how to do that. But the goal is to sort of test that in the future. So right now, the predator and prey that we have in question, Pseudomonas fluorescens and the protist, is growing together, and there's some plots of them growing together. These are just bacterial numbers for different controls. And if there's no additional food as you expect, there are these cycles, right, Lactovolterra type. And now the question is when we bring in additional food, what will happen? That is Sureni, current grad student. She's working with a couple of undergrads, and this is Bailey's lab. And she has actually assisted with a bunch of the experiments, although she's a mathematician, so I think of her as the so-called next generation math biologist. She's getting her PhD in a math department, but she can do a few experiments. Right? She can, if she goes into the lab, it's not that she breaks everything. She can actually generate a few of these plots. But thanks for your attention, and I will stop here. I'm happy to take questions and continue this discussion with anyone interested later on through emails, Skype, whatever. But thank you again for opportunity to talk, and I welcome any questions also. So thank you. Thanks again.
Thank you very much, Professor Rana. Wonderful talk, wonderful pictures, and a great video. I mean, that is the muscles being attacked by, covered up, and that was really nice to see.
Thanks.
I mean, that explains the things in such a good way
Right.
to all the listeners who might not be very much acquainted with the modeling, but
right.
all of them may get interested in doing some sort of mathematical modeling.
Right.
So I request any of the listeners, if they have any questions to Professor Rana, may come up with that. So if not, we have an email ID of Professor Rana to everyone. So if anyone wants, may contact Professor Rana. He's doing.
Yes, please feel free. If you want to contact me, please feel free over email, Skype, chat, anything. We can discuss in detail if you want.
So I hope listeners and attendees would be benefited with the presentation and the talk of Professor Rana. Professor Manjul Gupta is here. We can see her if she has anything to say. Ma'am, your voice is mute.
I got some messages in the chat to send the PDF of the presentation. So I can email you, Dr. Mathur, I can email you.
Sure. Thank you. So nice of you.
The thing is, it has really been, now am I audible?
Yes.
Yeah.
So it has been a good talk, that's what I would say, but what I would like to know, that in what way you connect pandemic with this, whatever you presented, in fact. That is what I would like to know, and then you can answer it later, not today. But I think the students must have been benefited, those who were listening to the talk, they must have been benefited by your presentation, that's what I feel. Anyway, thank you very much, Professor Rana. And maybe The next speaker. I will get. You are in Iowa,
I
right?
am.
Iowa
I am
State.
in Iowa State. Yes, yes.
Iowa State. Actually, I was in Iowa City that time. Long back.
University of Iowa.
The University of Iowa. So it was long back, 82, 83. So it's a long back. But that's really, really good. Okay. Thank you very much.
So, when I requested Professor Rana
Mm-hmm.
to give a talk on pandemic and mathematical modeling,
Mm-hmm.
he said that he's not an expert for that, but I
Okay,
have
so
seen
that
it
part I
and
missed actually. Mm-hmm.
I tried to work with him on a mathematical model, and
Mm-hmm.
the way he looks to the problem and the way he tackles that was really, I mean, that was something very new to me. And as such, because of although the theme was pandemic, but mathematical modeling was included in it, I requested him to go with some mathematical model, and at last, I mean, he connected that with the model, with the pandemic. That means susceptible and infected by taking the SI model, and
Mm-hmm.
so I'm very much thankful to Professor Rana for his great lecture, and hope we would be in touch with him, and hope that he will enlighten us with his research.
Yes,
Uh,
hope I can visit sometime. Hope once this whole
That would be better.
situation.
In fact, in person things are much better. That's what I feel. If
So,
you visit and then give a talk in the department, that would be a great idea, in fact.
absolutely, absolutely. Once this
Because,
situation, global
because
situation is sorted.
the thing is, in online, in fact, presentation, sometimes, one loses contact because of internet or whatever it is. So,
No,
presenting in a personal
there's no
presentation is always
replacement
better.
for classical chalkboard presentation. Of course, right? This is number
Yeah.
one,
Do
best
you,
medium.
do you intend to visit India sometimes in future?
Uh, yeah, depends on situation. Depends on the situation. Next year, hopefully, maybe next year.
Which part of the country you come from?
Well, my parents live in Calcutta.
Oh, Calcutta. Okay. But it's not far. Situation improves. Please do visit.
I'm sorry, I just forgot to introduce Professor Rana. Professor Rana is a mathematician. He has done his PhD from IIT Roorkee,
Mm-hmm.
and I mean, Professor, if Rana Saab can say a few words in his introduction, would be great.
No, no. My PhD is not from IIT Roorkee. It's from Florida State in the U.S.
Okay,
Oh,
okay.
Right.
okay.
Yeah. So I have been in the U.S. for many years since my undergrad was in the U.S. At New York, and then I did a master's in Maryland, and PhD in Florida State, and I was postdocing for a number of years at Clarkson, and then I was in Saudi Arabia,
Mm-hmm.
Okay.
and
So you
then
are something like
faculty.
IIT.
I was a
Then more or
yeah. I
less
was
you are an American, right? American citizen, I suppose.
yes. Yes.
Oh, great, great.
Okay, I do visit US sometimes because our children are there. So maybe I can get in touch with you sometimes whenever I visit. Okay,
Sure
thank you
thing.
very much.
Sure thing.
Okay, thank you very much, Rana sir. Thank you,
Sure,
thank
sure,
you,
sure. Thank you. Take care. Thanks again.
thank you. Bye.
Thanks a lot.
Okay. The next talk which we intend to hear is from Professor Arvind Kumar Mishradi from BHU, and I hope he is here with us. Yeah, Professor Mishra,
Yeah,
can you hear me?
yeah, I can
Oh,
hear
wow.
you.
Good to
Okay,
see you.
how are you?
Good to see you in this lovely morning. Very good morning,
Okay,
sir.
thank you. Good morning, ma'am.
Good morning, bhai. Arvind. How are you?
Okay. Fine, fine, ma'am. How are you,
Something,
ma'am?
Okay.
something is interrupting your video. I mean, there is some black thing coming just below your face.
Okay, then what to do? Okay, let me change the view. Okay. What about now?
No, that was good. You were at a right position, but I feel some wire or something is in front of your camera.
Okay. Actually, I have put one link for this presentation, so that's why this is
Okay,
happening. Okay.
no issues, sir. No issues. You carry on with your. So I welcome on behalf of Bharat Ganit Parishad myself and all the executive members of Bharat Ganit Parishad. I welcome Professor Arvind Kumar Mishra ji to deliver his talk. And without wasting any second, I give the control to Professor Mishra ji.
Okay. Thank you, Mathur Sahab, for giving me opportunity to present my work. Okay. So I am going to present now. Yeah, Pankaj ji.
पापा नाम बुलाया आपका
Pankaj Mathur ji.
Yes, sir. He is not available right now. Your screen is visible, sir.
Yeah, okay. Thank you.
Okay.
So that's why I wanted to know that whether it is visible or not.
Yeah.
So today I am going
किसी ने
to speak
संभाल
on
लिया
the pandemic COVID-19. So the basic talk on this topic is basically I will explore the effects of broadcasting, the advertisements through TV, radio, social media, etc. So first of all, I would like to say a few words about the advertisements and social media. What does it mean?
Sorry to interrupt you, sir. Sir, you can double click on your screen so that it comes in full mode, sir. The
Okay,
presentation.
Control L. So let me enlarge it. It is not
Okay.
happening so.
Yeah,
Okay.
sir. Yeah.
So now it is visible.
Yeah, sir. It is visible now.
So actually in 2000, the story begins in 2011 when I have started to modeling the role of advertisements, media programs on the control of any infectious disease. So what is happening when any disease is spread in the community? So if medicines are available, then people will go towards the doctors, so they will seek to the doctors and then they will take the medicines, etc. But that is also a costly affair. So to get a treatment, so that's why people say precaution is better than cure. So what precautions? If you are taking some precautions, what will happen? You will not contract the disease. This is the main idea behind this. Then how to aware the population? That is another question. Another question is whether people are responding towards the awareness or not. This is again a question mark. And then how to make the people aware? This is again a big question. So what is happening in 2011 when this pandemic was not there? I have started to think about that. That okay, how can we write a model in this regard? And I have started to make some literature search on this topic, and I got that okay, few papers. Then people were talking about the media. Okay, if there is a number of infected individuals or more, what will happen? People will take some precautions. Then they will try to reduce their contacts with the infected individuals. So what is happening? Basically, they have taken the basically the contact rate between susceptible population and infected population as a decreasing function of infected individuals. So that was the basic idea behind this, and this model was published in 2009 in International Journal of Biomathematics. Then after this, basically, I read this paper seriously, and I got that okay. So let me start in this particular topic, and then I have introduced a question, separate question for the media programs, and then I basically took that, okay, our population basically, when some advertisements through media comes, what will happen? People will become aware, and then they will form a separate class. That is, I have called them as aware class. So aware class has the tendency that they will avoid basically their contacts with the infected individuals, and then they will not contact the disease through the direct contact with the infected individuals. What will happen? Then only the susceptible individuals and infected individuals will contact each other, and then they may spread the disease. So that was the basic idea, and the equation for this media awareness program was first introduced at the international journals by us in 2011. That paper was published in Mathematical and Computer Modeling, and that was basically very basic paper and very simple paper. It and every student, I will suggest that if you want to start any modeling and this awareness program, then one should read this basically paper. This is very good paper. You will find it interesting also at the same time. Then basically idea was basically very simple, that the number of media programs should run proportional to the number of infected individuals in the community. So I have taken programs is proportional to the number of infected individuals. Suddenly in 2016-17, I felt that, okay, if you are making any advertisement on TV, what will happen? TV, basically, this is a costly affair. People will charge this TV programmers will charge you a huge amount of money. So why you are making only that? Okay, if most of the population is aware, so we should reduce the number of awareness programs. So that was the idea basically. So I have picked up this idea that number of TV programs are proportional to the number of infected individuals, but as a decreasing function of the number of aware individuals. So as soon as the whole population becomes aware, there is no need to make the advertisements on the TV. So the best example for this is the polio eradication. So what happened? So right now, if you will open your TV, you will not see any advertisement on polio. Only one or two advertisements within a 24 hours. You will say that, okay, this is the advertisement for polio, 2 drops for the life. So initially, when we have started it, so what government did? Government was making a lot of advertisements on TV, radio, or on the newspapers. They have allotted a lot of funds for this to make the population aware regarding the polio eradication. But right now, because the most of population is aware, so generally people go for these polio drops. So there is no need to make any advertisement on this. So actually, these things we were aware the population to go to the hospital. But what happened in this case of pandemic, COVID-19, the situation was very worse. Why it is worse? Because there is no medicines. So if there is no medicine, if you are going to the hospital, you will not get medicines. What you will get little bit amount of medicines which are generally used for the other diseases. And then if your oxygen level is quite low, then you will get some oxygen from the in the hospitals. Only thing is that you will have to take the precautions. So what kind of precautions are needed? So generally, right now, I think nearly 70-80% population is aware regarding the precautions to take to stop the spread of this COVID pandemic. So generally people wear the face mask, people follow the social distancing. Of course, I am talking about the educated people. Some people are not following the rules. That is a different issue. But government has made a lot of advertisement for this. Still, government is basically making some advertisements on the TV. I am also saying that only some leaders are coming on in front of the basically in TV to to say that okay, social distancing is quite important to stop the spread of this pandemic. Wearing a face mask, some government, some in some states, this is compulsory. People are also advised to um, go for the health checkup, and all those things are happening in the community just to aware the population. So we are making some advertisements through TV, through print media, on radio. Even then, sometimes we are also, when we are dialing on any mobile number, we are listening that, okay, these are the precautions which we should take to control the spread of this pandemic. So the reason behind is to pick up this topic because I have already worked on this particular topic awareness programs on advertisements, and this is most relevant to the right now in the situation COVID-19 pandemic. So I have thought to focus mainly on the broadcasting through advertisements on this COVID pandemic and through TV as well as through social media. So this was a little bit introduction about this. So right now I'm going to start formally that what we mean it and how to model it. Several researchers have made their models, published their papers. I have modeled it in a different, little bit differently because no one has talked about this awareness and advertisements, all those things. I was saying that how to get the data and how to, based on this data, how can we model it? Because still, I personally feel that the whole dynamics of this virus is still unknown. So, with this, whatsoever we have read on the newspapers or in some published articles, I have tried to model this COVID pandemic. So this is the outline of my talk. So I will present only one model because I have only completed one problem because Pankaj Mathur told me that okay, you will have to speak on this COVID-19 pandemic. So I thought okay, I should focus on this particular topic. So I have only going to make presentation for one model. So first I will give a little bit introduction about this COVID pandemic and then we will present a mathematical model and then we will do some mathematical analysis like positivity and boundedness of solutions because this is quite important to prove that all the solutions are positive and they are bounded. And then we will talk some epidemiological terms like disease pre-equilibrium and basic production number. And then we will talk about the endemicity of the disease. That is, we will try to find out the endemic equilibrium, and we will perform its global stability analysis to know that what will happen in future. And third thing is then we will do some numerical simulation part to support our analytically obtained results as well as to give some future insights that what results can be drawn from this modeling phenomena. Then we will talk about the conclusion and this conclusions, and some discussion will also take place. So, first part is infectious diseases are a major threat for mankind and globalization of world has accelerated the spread of infections rapidly across the world in a short period of time, which affect the public health care as well as hindrance the economic development of the developing and underdeveloped countries. In fact, I was seeing the first lecture of this conference that was quite interesting. Economy of lockdown. So naturally, you can see that the whole data of the world that economy of most of the countries GDP is negative for the most of the countries. Why this is happening? Because of the lockdown, because of the COVID-19 situation. What is happening? Most of the population is afraid. People are not going to their work. Or what is happening that if someone is going for their work, what is happening? He is working with half efficiency. So naturally, the GDP will go down. So that's why people are trying to get the vaccine. Scientists are working in this particular area that okay, we should provide the vaccine to the population so that the economy can be accelerated again. So this is the basically one should work on this particular topic, how this pandemic has affected the economy of any country. You can also think about this developed countries or developing countries or underdeveloping countries. So COVID-19 is working havoc on the whole world at present after its emergence in Wuhan in December 2019 and then global spread since February 2020. So what it has started in December 2019 and then it spread in the whole world nearly in February 2020. So how this spread has been taken place so fast? Some virus which was observed in December 19 in Wuhan, a city of China, and spread in the whole world in 2020 because of the travel of the population. Most of the population has traveled from one place to other place, and they were not knowing. Unknowingly, they have traveled. The symptoms were not visible. They were unknown about the spread of the disease, that how it spreads. So what happened? Unknowingly, this disease has spread in several parts of the world, and right now it has affected whole world, and so many persons are dying because of this particular virus. So the disease being caused by novel coronavirus is a new member of coronavirus family. So this was little bit introduction. So I am just scraping some of the slides. So question is how mathematical modeling can help us to curb the spread of the infection. That is again a big question. Mathematical modeling, how it helps, at least what we can do, we can say something that, okay, if you will follow these kind of strategies, the disease burden can be lowered down. So to lower down the disease burden on any country, we can identify some key parameters. What are the key parameters which are responsible for the spread of the disease? So till now, till date, we do not have any vaccine. Because we do not have any vaccine, so what we can do? Only awareness among the population can reduce the spread of the disease. So basically, here our main target is to find out the key parameters which are responsible for the spread of the disease and how can we control these parameters? How can we reduce these parameters? That is an important question. So we will try to find out all this answer of these questions. So here I have written something in blue color, so you can read this particular line. So you will get that about what we are going to talk. So they means population are employing different modes of propagating information, including social media, TV, radio, internet, using various types of slogans such as "Stay home, stay safe." So right now, the once when lockdown has started, so we were seeing a lot of advertisements on TV. Stay home, stay safe. So don't go outside to your home. Generally, people are advised. Government also has forced the population to stay in their home. So the next slogan was be clean, be healthy. So this was just cleanliness is more important. So like cleanliness, like hand washing, etc. Sanitization basically. We are talking about that. The main motive of such social media campaigns is to stimulate people to adopt healthy sanitation practices, frequent hand washing, use of face mask, sanitizer, maintain social distancing, avoid touching eyes, nose, mouth, etc. So the thing was that only thing this virus can you can inhale either through nose or through mouth, or the main sources of this is suppose you are touching any surface. So if the virus is there, what will happen if you are suddenly touch your eyes or nose or mouth? What will happen? Your virus can go inside your body, and then it will multiply inside your body, and then you will become infected, and after that you can infect the others too. So that's why to stop this disease, what happened? Government has mainly focused on this particular sanitization practices. So generally, we should follow all these practices so that we can not contact the infection, and we will not be able to spread the infection. So that is the thing. So these are the few models. Chang et al. Have assessed the impact of media coverage on the spread of COVID-19 in Hubei province, China. Continuous propagation of information through media campaigns is found to encourage the people to adopt preventive measures to combat the pandemic together. Findings of Zhao et al. Suggested that besides improving the medical levels, media coverage can be considered as an effective way to mitigate the disease spreading during the initial stage of an outbreak. So these are the important practices at the initial stage of the outbreak. So if number of infected, initial stage means if number of infected individuals are less, if a lot of advertisements are coming on the TV, so what will happen? People will not contact the infection. So, and then the infection will not spread in the community. Once the community spread will start, it will be difficult to control it. So that's why government imposed some lockdowns at the initial stage. So this was the study which was conducted by Zhao et al. However, the factors like very high population density, the unavailability of specific medicines or vaccines, insufficient evidences regarding the transmission mechanism of the disease also make it difficult to fight against the disease in India. The present study aims to assess the impact of social media advertisements on the transmission dynamics of COVID-19 pandemic in India. So, our model basically we have focused only on this pandemic, COVID-19 pandemic for India. We studied the effectiveness of social media advertisements in reducing the contact rates of susceptible and symptomatic asymptomatic individuals, hospitalization of symptomatic individuals, and quarantine of asymptomatic individuals, and flattening the disease progress curve. Our aim is to investigate how much these intervention studies can control the spread of coronavirus, and whether these control studies can eliminate the burden of COVID-19 in India. So our focus will be on last 3 points. So here is the schematic diagram. So this is a very big diagram. So you can see it clearly, then I will try to explain it. First try to grasp it. So for 1 or 2 minutes I will give a pause. So you can see that how the population is moving from one to other. Let me say something about this. S means susceptible population. S is susceptible population who can contract the infection. A is the exposed class. A is the aware class. Aware class means the population which is aware. IA means infected asymptotically. IS means infected symptomatically. H means hospitalized persons. R means recovered persons, recovered from the disease. Q means quarantine persons who are quarantined. M is the number of TV oblique social media advertisements. So this is the schematic diagram. How the population moves from one class to other class. So right now you can see.
ikut kayaknya ya. Papa,
So right now, I think all of you might have seen this particular schematic diagram. So right now, I am going to explain it. So lambda is the immigration rate to the S class, whether through by birth or from some other places, because we are going to model this for India. So persons from the other countries can come to the India. So A is the rate of immigration. Simply say that from the outside, either through birth or through from outside, they are coming to the susceptible class. D is the natural death rate. Whether a person is infected or not, he will die approximately at the age of 60 or 70 years. So average lifespan of the population is human population is 70 years. Then D is the natural death rate. So naturally he will die out. So this D will occur in all the classes, whether in susceptible population, whether in exposed class, whether in aware population, whether in asymptomatic infected class, whether in symptomatic infected class. So D is the natural death rate. So right now what is happening? Population, susceptible population moves to the exposed class at a rate beta 1. When the symptomatic persons comes in contact with S class, or if there is any contact between susceptible individual and symptomatic infected individuals, what will happen? It means he has exposed to the virus. So beta 1 is the contact rate, transmission rate from S class to E class. So if we ignore the effect of advertisements, what will happen? Ignore the effect of the advertisements means we are taking M to be 0. So if beta 1 is the contact rate between S and IS, what will happen? The population will move from S class to E class at the rate beta 1 SI, S into IS. So what is media is doing? Media is doing what is that this contact rate beta 1 will be a decreasing function of media advertisements. So if population is seeing the advertisements, so if we are seeing the advertisements on TV, if any person who sneezes or who is having a fever, what will happen? We will try to maintain the distance from that particular person, or we will move away from that person, because we are trying, we know that we can contract the infection. So this is the effect of media advertisements, that we are trying to reduce our contacts with the symptomatic persons. So that's why we have taken beta 1 into 1 minus CMS m divided by p plus n. We have taken the decreasing function of beta 1 as a decreasing function of m, but we have taken m upon p plus n. Why we have taken? This is a saturated function. We are highly basically aware, we are running a lot of number of advertisements on the TV, but still if there are some marriage ceremony or something like that, and some symptomatic person comes, we say, okay, he might have some usual fever, or he might be sneezes due to some seasonal variations, etc. So basically, we are aware, we know we have seen so many advertisements, but still our response is not too much. So that's why we have taken here, if m goes to infinity, what will happen? M upon p plus m will tend to 1. So at that time, beta 1 will become 1 minus CMS. But if we will take m to be 0, what will happen? This will be simply beta 1. So we have taken a decreasing function of beta 1 as a decreasing function of m, but following a Halley type 2 interaction, or say that saturated type of function. So this is the movement from S class to E class. Okay. Second movement is from S class to E class due to the asymptomatic persons. Because this virus, you may get the symptom. Symptomatic means you have symptoms, like you are sneezing, you have fever, or you have whatsoever the symptoms are visible are known to us regarding the COVID pandemic. So if those symptoms occur, we will call that this particular person is symptomatic. And if no symptoms are coming, but still they have the virus inside their body, we will say that this is a symptomatic person. So IA is basically a symptomatic person. So there are contacts between S the movement is from S class to E class due to the contact between the susceptible individuals and asymptomatic individuals. So we have taken beta 2 as a transmission rate from S class to E class because of the contact between the susceptible individual and the asymptomatic individuals. So this is also we have taken a decreasing function of social media, public TV advertisements. Here again we have followed the Hurling type 2 interaction or saturated type of function because of the same reason as I have given it earlier. So right now you will say that why we are not taking beta 1 to be same as beta 2? Why we have taken CMS and CMA? So the reason behind this is that if a person shows some symptoms regarding the disease, suddenly we will try to maintain our distance and we will try to move away from that place. But if a person is asymptomatic, our mindset is like that. Okay, he may not have a disease, so we will be a little bit liberal about that, and then we will not avoid our contest too much. So that's why we have taken beta 1 and beta 2 to be different. Of course, beta, here we have taken CMS and here we have taken CMA because of the same reasoning. Here decreasing function will be more, here it will be little bit less. And D is the natural death rate in the exposed class. What is happening from the exposed class, the person who is exposed to the virus, either they will develop a symptom or they will remain asymptomatic. So what is happening? The movement is from E class to IA class and the remain rho sigma A, E is the movement from the E class to IA class, and then 1 minus A sigma E remaining portion goes to the symptomatic class. So if you will take A to be 0. What will happen? If A is 0, it means whole population in the exposed class is moving towards the asymptomatic class. If you will take if you will take A to be 0, the whole population in the E class moves to the symptomatic infected class. If A to be 0, A to be 1, what will happen? The whole population will move to the IA class. So generally A is the fraction which determines how much population from the exposed class moves to the asymptomatic class and how much fraction moves to the symptomatic infected class. Of course, the asymptomatic population generally, if you came to know that you have basically some contact with the persons who is diagnosed to be COVID-19, so generally you will quarantine yourself at your home. So the persons from the IA class, they will quarantine themselves, or government force them to quarantine themselves. So the movement is from IA to quarantine class. Of course, if you have symptoms, what will happen? You will be hospitalized or you will go to the hospital, then the movement from the IS class to S class at a rate 5 years. Of course, here is the death rate, natural death rate, DIS, and because you are symptomatic, so the person who is symptomatic can also die. So the death rate will increase. So this is the basically alpha IS is the disease-induced death rate. So generally we are seeing on the newspaper or we are also seeing the data which is coming on the internet. We are saying that so many persons have died because of the COVID-19. So this is the disease-induced death rate. And then from the hospitals, people will again die in the hospital. So this is the again alpha S during the treatment. So this is the death rate in the hospital who are the infected individuals. And right now the movement from S class to R class, persons are required in the hospital and then they will join the required class. From the quarantine also, people will become required and then they will join the R class. And this is the natural death rate in R class. Of course, after recovery, I am not very much sure, but I have read because in the some articles that after recovery, people may also contract the infection. They can also they may be also susceptible again. So the movement is from R class to S class we have taken. So they may again become susceptible after the recovery. So this is the dynamics of the COVID-19 pandemic, which I am going to present over here. So generally, because we have, we have not talked about A class. A is the aware population. So what is happening? We are basically focusing on the media programs. So what will happen? People will become aware regarding the disease, and then they will form an aware class. Because of the aware population, because we are fully aware, then we will not contract the infection. So we have not taken it. Of course, if someone wants to generalize this model, he can generalize by considering that A can also contract the infection, but at a lower rate in comparison to the susceptible individuals. We have considered DA as the natural death rate. We have also considered lambda 0A. Okay, people's population is aware. That is correct. But at the same time, because of the social norms, we are aware, population is aware, but it is again going to the social gatherings, where social distancing norms are not followed, or people are not wearing the social masks, etc. Then at this rate, lambda 0A, population may become, aware population may again become susceptible. So because of the forgetfulness of the awareness programs or media advertisements or the awareness, people of the A class may again become susceptible. And once they will become susceptible, what will happen? They can form they can contract the disease. Then the whole dynamics will be repeated for this class too. Right now, we are talking about the M class advertisements. So you can see that we are introducing basically we are making the advertisements proportional to the number of symptomatic individuals. So because we don't worry a lot about the asymptomatic individuals, if symptomatic our population becomes zero, government will not make any advertisements, because right now asymptomatic persons, and then they know that okay, they will require, and then they will again go for their work. Because of the symptomatic persons, they are also got hospitalized, and all those problems have started because of the symptomatic individuals. So that's why we have taken the number of TV advertisements and social media advertisements proportional to the number of symptomatic infected individuals. So I have taken R into IS, and then they are basically, we have taken this factor 1 minus theta a divided by omega plus a. Why we have taken this factor? Because to make any advertisements is a costly affair. So if the most of the population is aware, so we reduce the number of awareness programs. Okay, so we have taken this R as a function of A rather than a constant. So you will say that if A is 0, it will become R into IS. As soon as it increases, what will happen? This function R 1 minus theta A divided by omega plus A will be less. Basically, it decreases as the number of aware individuals increases in the community. So this is a decreasing function. Again, this is a saturated type of function we have taken. Again, we have taken that, okay, some advertisements do not, basically, they cannot be too attractive, or they may not be impressive. So they are unable to motivate the population to get aware. So the number of TV advertisements, social media advertisements decreases at the rate R0 M minus M0. M0 means we have taken the baseline number of awareness, baseline number of TV public social media advertisements. Baseline means whether the infection is there or not, M0 number of advertisements will also be will always be maintained in the system. So at least for polio, you can say that okay, 1 or 2 advertisements per day we are seeing on the TV or on the newspapers. So this is basically M0, baseline number of TV public social media advertisements, which are always maintained in the system. So this was the dynamics for the social media public TV advertisements, and this is the dynamics of the COVID-19 pandemic. And basically, we have merged these two. That's why we are getting these terms beta 1 as a function of m, beta 2 as a function of m, and the movement from S class to A class also depends on m. So if you put m identically to be 0, you will simply get the dynamics of the COVID-19 pandemic in absence of media, TV advertisements, social media advertisements, etc. So this was about the schematic diagram of the model phenomena. Then we can easily write this into the model equations. Here we have considered the variables. S is the number of susceptible individuals, I have already told you. A is the number of exposed individuals who are exposed to the virus. Is the number of symptomatic individuals. IA is the number of asymptomatic individuals. Of course, I and represent the number of infected individuals who have symptoms or who do not have the symptom. Q is the number of quarantined individuals. A is the number of aware individuals. S is the number of hospitalized and are notified individuals. R is the number of recorded individuals. M is the cumulative number of social media advertisements. Here are some model assumptions which we have considered. I have already told you most of them. So I am basically not going to focus on this. I want to come to the model equations directly. So here is the model, complete model, how we are going to write it. On the once if you have understood that schematic diagram, you can easily write down the equations. So the C, ds by dt is lambda. So rate of the immigration, then the population from S class moves to the E class. So beta 1 1 minus CMS m divided by P plus M S into IS. This is the contact between susceptible and symptomatic infected individuals. So the movement will be from S class to E class. This is the movement from the S class to E class due to the contact between susceptible and asymptomatic infected individual. So they are from the S class to A class. Lambda SM, the effect of media advertisements, what will happen? People will become aware, then they will move to the A class. That's why lambda SM from here, population moves to the A class, so we are getting lambda SM over here. Again, lambda 0a, basically the forgetfulness because of the social norms, etc., the aware population can also become susceptible again at the rate lambda 0. So from here, we are getting lambda 0 minus term, here we are getting plus term. Delta R, basically the person who is recovered from the disease, they can again become susceptible at a rate delta. So the movement is from R class to S class. D is the natural death rate and which will be common for all the classes. So this is the S class, you can say sigma E. Here you can see that some fraction of it go to symptomatic class, some fraction go to the asymptomatic class, and again this is the movement from the symptomatic class to the asymptomatic class, and asymptomatic class to symptomatic class. This is the disease-induced death rate, and this is the IS already to the hospitalized population at rate 5S. So the movement is from IS class to H class. S is the recovery rate, alpha is the disease-induced death rate. All those terms I have already explained, and this is the equation for M. So this is a 9-dimensional model. It is highly nonlinear in nature. So it is very difficult to solve to get the analytical solution of this mathematical model. So what we are doing, rather than trying to get the analytical solution, what we are trying, we will try to study its qualitative behavior. Qualitative behavior means what will be the long-term behavior of the solutions. Basically, where we will reach if your time is very large. Okay, so we are going to apply some techniques. For this, we will try to find out the equilibrium solutions. So equilibrium solutions are equilibrium points, you can say, by setting the growth rate of all the dynamical variables to be 0. ds by dt is equal to 0, d by dt is equal to 0. All these derivatives we will put to 0, and then we will try to find out the equilibrium points, how many equilibrium points we will have. So we are most interested that, okay, can we achieve the disease free equilibrium? And how can we achieve the disease equilibrium? How can we reduce the number of infected individuals? These are the questions which we will try to answer on the basis of qualitative analysis of this mathematical model. This is the description of the parameters. So lambda is the immigration in class of susceptible population. I have person per day. Beta 1 is the contact rate of susceptible with symptomatic individuals in absence of awareness programs per person per day. And all those I have already explained you that parameters while explaining the schematic diagram. So these are the parameters. So right now using the fact that S plus E plus IS, all this sum of all these individuals is equal to N. So N is the total population. Whether a person is susceptible, population is total human population of that particular country or particular region, you can say. So we have taken N to be S plus E plus IS plus IA plus Q plus A plus H plus R. So by using this, we can get this set of equations. So basically, once you know that what is the value of N and all those things, you can compute the other variables. Okay, so here you can see that we have not considered S class. But if you know that what is N, what is E, what is IS, all these variables, then you can easily find out that what is S. S is will be nothing but N minus sum of all this population. So that's why this is a reduced system. If we find study the dynamics of this particular system, this is equivalent to find out the dynamics of our original system. So we have obtained that our solutions are bounded, and we have obtained that the E, IS, IA, Q, A, H are always less than or equal to N. So generally, whether you will consider to explore class or you will consider IS class or IA class, naturally, because N is the sum of all these quantities, so naturally one particular number of individuals in particular class will always be less than or equal to N. Of course, N is less than or equal to lambda by D, so naturally all these components are bounded. And we have also found that M is less than or equal to M0 plus R lambda by R0 D. So here we have obtained a disease-free equilibrium. Disease-free equilibrium means where disease is not there. No symptomatic person, no asymptomatic person, no hospitalized persons, no quarantine person, and disease is not there. So what is happening? This becomes 0, 0, 0, 0, all these components, and here this number. Then lambda by D is the total population. This is the aware population. Of course, lambda, small lambda, capital lambda, M0 divided by this is the aware population. Lambda by D 0, 0. Because M0 I have already told you that M0 is the baseline number of TV public social media advertisements. So they will always be maintained whether disease is there or not. So we have considered this. So we are getting M0. So we are short in time. So we have obtained the value of R0. R0 is the basic reproduction number. You might have heard Rajesh Bhushan on the TV when he was talking about R0, the value of R0 is greater than 1. So generally what is happening, R0 means basic reproduction number. What is basic reproduction number? Basic reproduction number tells us if the whole population is susceptible and one infected individual comes in that community, what will happen? How many persons will be infected by this one particular infected individuals during this total infectious period. Suppose one person who has COVID-19 and his infectious period is 14 days. So during these 14 days, one infected individual, how many he has infected, how many individuals of the susceptible population, where whole susceptible population is basically population is susceptible. There is no other infected individuals. So naturally, if R naught is greater than 1, so one person infects more than one person, then disease will spread. If R naught is less than 1, what will happen? One person infects less than one person. It means two persons, when they are in the community, they are able to infect one individual, so disease will generally die out. So if R0 is greater than 1, disease will certainly spread, but if R0 is less than 1, disease may die out. So there is some other factors. I am using the word may because of the fact that there may be a possibility of backward bifurcation. So sometimes what is happening if R naught is less than 1, still we are unable to eradicate the disease. That's why we have said the word R naught. But it is sure that if R naught is greater than 1, it is difficult to eradicate the disease from the population, from the community. So we have derived this local asymptotic behavior, and we have also derived the endemic equilibrium. So I'm escaping this proof of this mathematical proof. We have also shown the global asymptotic stability of endemic equilibrium. We obtain the endemic equilibrium E star if feasible is globally asymptotically stable inside the region of protection if the following inequalities are satisfied. So we have used the Lyapunov's stability theory to derive these conditions. So anyone interested can basically read the book of Professor M.R.M. Rao. So he has written a very nice book on the stability theory, differential equations. So here is the proof. So here we have basically tried to estimate some of the parameters for our country India, and we have tried to demonstrate that which parameters are most sensitive. So we have obtained that beta 1, beta 2, sigma, lambda, lambda 0, alpha s, d and r0 are the sensitive parameters, and we will try to estimate these parameters by using the root mean square error. So we have estimated parameter values. So few of the parameter values are available in the literature, and some we have estimated. So like lambda we have assumed this, beta 1 we have estimated, beta 2 we have estimated, CMS we have assumed, CMA we have assumed, because regarding this TV advertisements, social media advertisements, it is very difficult to find out that how many times they have shown the advertisement and what is that impact. So once the whole data will be available, then you can also estimate these parameters. So here basically plots of the output of the fitted model 2.1 and the observed active corona cases of India. So we have taken the data up to September 7, 2007, and then from the April 1, and we have got that this red is the actual data, cumulative number of confirmed cases, and this is the model simulation. Model simulation, blue line is the model simulation, which model basically predicts, and this is the actual data. So here are the equilibrium values which we have obtained. Here the graph for the global stability we have obtained. Here we have got we perform the sensitivity analysis to test which parameters influence the most symptomatic infected population. Our basically focus is on the symptomatic infected individuals. So we have tried to find out the parameters which are most sensitive towards the symptomatic infected individuals. So you can use automatic differentiation method. We have used code for this, and this is the formula which we have used for the L2 now. And this is the graphs which we have obtained for the semi-relativities sensitivity analysis. Of course, this is quite small, so it is difficult to be visible. So let me try to put 400. So some of you can say that how beta 1 is going to affect, why lambda is going to affect, how CMS is going to affect. CMS, initially the population was this, and then if you increase CMS, what will happen? This will decrease number of symptomatic individuals, then again it will start to increase. And then finally it will come over here. We have taken time to be 0 to 400 over here. So again, similarly, we have taken so many parameters for how they are going to reduce it. And this is, we have plotted the sensitivity quantification by calculating sensitivity coefficient through L2 norm. And here we have obtained, you can see these results. So our case yields ordering sigma R0 D beta 1 alpha s lambda phi s r lambda 0, that is out of the 24 parameters only the first 9 rank parameters are the most identifiable and sensitive parameters. These are the parameters which are more sensitive. So we should focus to reduce the number of infected symptomatic individuals in the community. We should focus on these parameters. So generally, this is the normalized false sensitive indices of R0 with respect to model parameters. So what is happening? R0 basically basic reproduction number. So our target is to reduce the basic reproduction number. So you can say that the parameter lambda, if you will increase the parameter lambda, what will happen? Your basic reproduction number will increase. If beta 1 increases, what will happen? Basic reproduction number increases. If you increase CMS, same as the effect of media. What will happen? Basic reproduction number will decrease. Again, the increment in sigma will increase the basic reproduction number. So this is how the parameters are going to affect your basic reproduction number. We have done it. We have obtained the results. So here are some graphs that how R0 is affected by lambda and M0. These are the parameters which are related to the social media public TV advertisement. How CMS and phi S are going to affect the basic reproduction number. So these are some plots, contour plots we have obtained. And here you can see that effect of variation of symptomatic individuals IS with respect to time for different values of R and M0, and second graph is for phi S and lambda. So you say that a different combination of R, if you will take R to be 0, M0 to be 0. So there is no effect of media. So number of symptomatic individuals may reach up to 2 into 10 power 5. But if you are not going to increase the number of social media TV advertisements, basically you are taking R to be 0. If you have some baseline number of social media TV advertisements, you will be somewhere here. So your right now it is 1.3 into 10 power 5. And if you are taking R to be 0.001, M0 to be 0, you are here. If you are taking R to be 0.05, M0 to be 1000, you will be here. It's just same line. So these are combinations we have tried. Of course, these are not the estimated parameter values. Here we have taken the effect of these parameters to demonstrate the effect of these parameters on the number of symptomatic infected individuals. So here are some conclusions which we have done. So we have tried to find out some important key parameters because my time is over. So right now this is again over nearly. So these are the conclusions which have obtained. So here are some references. Some work has been carried out in this direction. And then finally, I thank my collaborators, Dr. Pankaj Kumar Tiwari, who is my ex-student, Dr. Rajnish Kumar Rai, is also my research scholar who has completed recently. So I thank both of them for doing this work. So thank you. So right now, questions.
Thank you very much, Mishra ji. Aapka lecture, as usual, it was fascinating, energetic, and those 9 equations with how many? 26 parameters, out of which
Yeah,
7 were playing a huge role in determining the effect of COVID-19 quarantine. The effect of media related, the effect of rather media on reducing the spread of COVID-19 and making the people more and more aware. That was really nice. The figures, that a single picture having all the parameters drawn and their variations, it's not easy, it's very difficult. Thank you very much,
yeah.
sir. I invite questions from the listeners. If they have any queries, please. I don't think anybody is having any questions right now. All of them are demanding many of the listeners are demanding your presentation. So I
Okay,
would,
I will send it. I will send it, Pankaj.
I would request. Thank you very much, sir. Thank you very much, sir. Thank you.
Sure, sure, I will send it to you.
Madam,
Actually, when we are talking on this online, basically face to face is something little bit eye
no,
contact is very necessary.
yeah. That is
So
a must.
I was
That
little bit sometimes in the meantime I was little bit discouraged whether what is happening or not. Actually, I
no,
was able
is
to see the
anybody is
faces of
listening
all
or
the
not?
candidates.
You're
The power
right.
also went off, in between. That's also there. So
Yeah,
such problems are definitely there.
yeah.
But are you collaborating with Prashant Srivastava?
Not now.
Acha, acha.
On
Okay.
this particular topic, I have not collaborated, but earlier we have written few papers in collaboration with Pankaj, with Prashant.
Prashant. Okay.
Yeah,
Okay.
on Kalra model actually.
Because
On
he's
Kalra,
also working on this line, and yesterday he had presented his work. So, of
yeah,
course, his parameters were less than what you considered, if I remember correctly,
yeah.
right? So, I mean, if you increase the number of parameters, then
Yeah.
how your model is being affected?
Yeah, actually, once you increase the number of parameters, it is difficult to basically make the predictions. Only thing is, then we are not able to perform our whole mathematical analysis.
Mm,
Generally, we go for this simulation. So that's why we have estimated the parameter value. The idea was this because this COVID-19 pandemic, some data was available on the internet, and Pankaj Tiwari actually he did his PDF at ISI Kolkata and visited to Italy also. Then he learned something regarding the estimation of the parameter values. Earlier, I had not written papers on the estimation of the parameters. Then he said, okay, sir, make a good model so that we can be able to advise something regarding the spread and control of these behaviors. So that's why we have considered so many parameters. Only the thing was that the main focus of this model was to estimate the parameter values and to give some idea regarding the real situations of our country. So that was
okay.
the thing.
No, that's good. But is your work confined to India only, or is it global?
It is general model, but simulation is only for India because we
No, the
have taken
data
the data from the
from
Indian.
India.
India.
That's good. That's
Yeah.
good. Okay. Anyway, it has really been a very good talk, and I think you presented the things very well, as usual, what Pankaj Mathur has said.
Thank you, ma'am. You people have taught me a lot, so I have tried to
Anyway,
demonstrate in
thank you.
front of you.
We feel happy whenever
I,
you
I, I,
write. Actually,
I have attended so many classes in room
Mhm.
number 501, I think, at IIT Kanpur, and you taught me during MSc. Two courses I have done with you.
Oh,
So
thank
that
you.
was a nice job. Okay.
Anyway, you are our ambassadors. That's what you could say. I feel students are always ambassadors of teachers, right? As far
Yeah.
as work is concerned. Okay, thank you very much.
Okay. Thank you. Thank you.
Thank you very much, Professor Arvind Kumar Mishra ji,
Mhm.
for
Thank you.
your great talk.
Okay. Thank you.
So,
I will send you the PDF. Okay, Pankaj?
sure. Thank you very much, sir. Thank you. Okay. So now we come to an end to this session where we have invited talk, and now we go on to paper presentation sessions. Uh, Varun, are you there?
Yeah, sir. So I'm
How
here.
many, how many people are there to present their papers?
Sir, I think so. 6 to 7 people are there to present the paper. And
Oh,
should I call the names as per?
sure. Just start them.
Uh, of Anand Ballabh Joshi, sir. Are you there? Anand, sir.
Anand Joshi ji, are you there?
Yes, sir. Yes, sir. Yes, sir.
Okay.
I'm here.
So,
Uh, Okay, sir, the title of the paper is Understanding the Spread and Prevention of Spread of Corporate Virus Using Graph Theory. So, sir, you can present.
So I welcome Anand Joshi ji. Anand Joshi ji is our colleague at the Department of Mathematics, and he is basically from the field of cryptography, and he is trying to study this new phenomena with the help of graphs. And I welcome him for his presentation. Joshi ji, Anand Vallabh Joshi ji.
Thank you, sir. Thank you very much. I would like to thank to Professor Pankaj Mathur sir and Professor Manjula madam and head of the department. And good morning to all of you. So basically, this is not a paper. This is just a talk. So because in most of the talk we have heard about the differential equation and the solution of the differential equations, system of differential equation. So, but now in my talk, just I want to give some incitement about the graph theory and how we can model this any pandemic using graph theory. So, this is a basic lecture, and this will help the student to make understanding about the graph theory and how to modeling of any pandemic using graph theory. So I would like to start. I would like to present the screen. So I would like to start with the definition and the social network modeling. So because whole world is suffering from this coronavirus pandemic, and a lot of work has been done on modeling of this COVID-19 virus and the spreading of the virus. And after
Sir, sorry
analyzing,
to interrupt you, sir. You can just double click on the screen so that the viewers on the mobile can easily see the presentation. You can just double tap on the screen.
I will just run it in full screen
Yeah,
slide mode,
yeah, yeah.
and after some time this I will convert into this mode because I will write on my pen tablet also.
Okay, okay, sir. Okay.
Okay. So this, so what is the social networking? So we have heard about the social networking. We all aware with Facebook and Twitters, but here we are not. I'm not talking about Facebook and Twitters. So social networking basically this is a group of people, right? Uh, this is a group of small people. This may be the group of the large peoples and the interaction between these groups. So this is basically the social networking. And social networking is basically a computational tool to track the human interaction, how the humans are interacting with each others, because the interaction of the humans is carrier of virus. So, analyzing the model of social network modeling, this help us to predict the spread of virus, and this also help us in making policies to reduce spreading virus. And social networking can be understand and visualized very well through the graph theories, because we have seen. the lecture of A.K. Misra sirs and some other lectures. Most of the modeling, mathematical modeling is based on differential equation, right? We have some system of equations, but it is very difficult to solve the system of non-linear equations. So we can think modeling using the graph theory. Basically, graph means the definition of graph is we have some set of vertices and we have some set of edges. And vertices, set of vertices means we also call the set of vertices as nodes. And there is an edge between two nodes, right? So this is one of the figure which I have shown here. This is some social networking models. There are some node in red color, some nodes, some vertices in green colors, and some in other colors. Basically, this is a population, and these vertices and these nodes represents a person in a population, and different colors show the different characteristic of a group or a subset of a population. So as I told you that in a population, each person is represented by a node, and edge between two nodes represent a connection between two persons. That is, if the person are interacting with each other, then there is a edge between two nodes. And any social contagious phenomena can be represented by graph theory. And so modeling using the graph theory help us to understand the phenomena of pandemic very well. So the virus are transmitted from person to person in a population. So studying the social network modeling in important in preventing the spread of the virus in a society. So just I want to give simple examples so that we can understand, we can visualize how we can apply the graph theory in modeling any pandemic, and in modeling any pandemic or any phenomena in which there is a spreading of virus. So there is a significant probability that an infected person will pass on the infection to some subset of the population he is interacted with, right? Suppose we have some population, for example, in this period, the coronavirus is spreading. If two persons are interacted, there is a probability that the virus can be transmitted from an infected person to non-infected persons. So this probability may be half, this probability may be 1/4, this probability may be one. That means a people of infected person can be infected to other person 100%. So it depends uh, on the uh, on the other nodes also. So suppose an infected person, in this example I am taking that infected person pass on the infection with half of the probability he or she is interacted with. For example, suppose a person is interacting with one person, then he can pass on the infection by half of the probability. So now to visualize what is going on, so we are talking the following examples in which an infected person interact with 8%. In this examples, I am taking that a person is interacted with 8%, and there is half the probability that the transmission of virus, there is a probability, half is the probability that the virus will be transmitted from one person to the infected person to other person, right? And R0 is basically this R0. So here this is a uh, R0 is the number of person an infected person may infect. And in these examples, I am taking a person is interacting with 8%, right? For example, suppose there is an infected person and this person, suppose this person goes to library, he goes to library and he interact with librarian, right? Suppose he interact with the librarian, so there is some probability that he will infect this librarian or the person which come in the contact. And suppose he goes to gym or any other places, and here he also interact with some other person, right? And he go to some marketplace or some other place, he also interact with the person, and he also he goes to some other place, suppose he goes to market or some other places. So these are the 4 person, 1 person, 2 person, 3 person, 4 person. These 4 person, he is interacting with infected person, he is interacting with this 4 person. And suppose he goes with his friend to some restaurant or some hotel, and these are the 4 person, he is going with all these persons. So here the person are represented by these nodes, and the interaction of a person is represented by these edges between any 2 nodes. This is the one node, infected node, and these are the 8 person, 1 person, 2 person, 3 person, 4 person, 5, 6, 7, 8. He is interacting in these examples to understand the phenomena how the virus is spreading. I have taken this 4 person. So these 4 person are interacting with each other. So there is a edge between all these. So this is a type of a complete graph. In a complete graph, there is an edge between any 2 vertices, right? So interact with each persons, and suppose, because in this example I have taken the probability is half. Suppose this infected person infect 4 person. Suppose this infect these 4 persons. Suppose he infect this person, infect this person, and he also infect this person, and the virus also transmitted from this person to this person, and suppose the virus is transmitted from this to this person, right? So that means this infected person infect 4 persons. So whenever there is this value of R naught, where R naught is the number of the people and infected person may infect is greater than 1, then the growth will be exponential, because this person, because uh, there is this is the one node, this is infecting the virus in 4 person, right? For in our examples, we are taking these 4 nodes which are the infected from. Initially it was the 8 person, from this infected person interacted. Now these 4 person are infected, and these we are taking in this example that every person is interacting with the 8 persons. This is some imaginary data. So suppose this also infect the 4 person, and this person also infect the 4 person. So these nodes are representing the person and the ages between the interaction between any 2 persons, right? So we can see that this is a tree, this is a tree, and the growth is exponential, right? So dot dot. So this all these. So the virus is spreading very fast. So this is from from 1 person to 4 person, then then 4% to 16%, and then 16 to 64, and so on, right? So this growth is basically exponential growth, right? So now what we can do? So how we can reduce the number of infected person. So basically in this time of coronavirus, we have heard about the social distancing and the sanitization, hand sanitization. If we frequently sanitize our hand, suppose this infected person, for this example, suppose this infected person interacted with this librarian, and suppose this librarian takes some preventive measures, suppose he takes some hand sanitizers, he sanitizes his hands, then the virus will not spread here, right? So that means then there will be no connection between these two. And suppose this person, and for instead of going to library, he can uh, read the books, online books, and he can take some other measures so that virus does not spread, right? So these are the some preventive measures which we can take. So now, so by using this graphs and by using this nodes, so we can analyze social networking, and we can, because in this example I have taken a small set of data, but the computer scientists take a large number of data, because in a population there are crores of the peoples, and in a city suppose there are millions of the people. So the data is very large, so it is very difficult to analyze and compute and make some conclusion about this data, but this will help to modeling the spreading of virus. So by modeling the social network using graph theory, we can track the human interactions. We have heard about the Arogya Setu app, and all these apps are basically uh, depends on the interaction of the peoples. Because suppose we have a population, we have a millions of the person in a population, and they will interact with each others. So then if there is an interaction, if the people is infected, that is there is the age between any two nodes. So this kind of application, there is some application, suppose making an app of tracking the human interaction and predicting about the infected person. So this will help us in such kind of modeling. So modeling social networks using graph theory will help us to predict the spread of virus, and in making policies to reduce the spreading. So there are some other definition or some other things we can apply in this mathematical modeling. First, there is a weight, right? By assigning the weight to the edges between two nodes, we can analyze the spreading of the virus. That is, if we take a small, for example, if you take a small household unit in which there are the four members. In these examples, we are taking the four persons in a family, and they are interacting with each other. Suppose there are four persons, there is a husband, there is a wife, and there is a mother, and there is a son, right? So these are the four person in a family. So because there is a more probability that the husband and wife, if the husband is infected, then wife will be infected. There is a more chance, right? and there is a less probability that the mother will infect from this because they are staying in the same room and they are interacting with each other. So we can give the weight 1 here, we can give the weight half here. Suppose the son is isolated in room or he is in some other places, and there is a we can give the zero weight to these ages, right? So by giving the this will help us to analyze the spread of virus. So giving the zero weight to an age means there this person, this son is not infected from this, and there is a 100% probability that virus will be infected. So we can give weight 1 here, right? So less weight means some kind of quarantine. Quarantine means that means this person is isolated from other nodes, or there is a no connection. There is no connection, there may be no connection, there may be no age between these two. But if there is a weight, there is an age, the weight on this age X is 0. Right? So this by giving the weight, this will analyze or this will analyze the help of this will analyze to spreading of this virus. And second thing, which is the clustering. Clustering means the small clustering means we can suppose we are using the social distancing protocol. That means that is the more distance between two people. This is one cluster. Suppose these nodes represent the excuse me. Hello. मैडम आपको तो हमने पहले भी बताया था कि बच्चे यहाँ पे रह रहे हैं, कई बार आपसे कंप्लेंट भी की थी और बच्चे भी।
सर आपकी टॉक चल रही है सर, यू आर ऑनलाइन।
आते रहते जाते रहते हैं वही हमने आपको पहले भी इस वक्त बताया ही हुआ था।
आई फील
हेलो, sorry for this interruption because I got some important from the university. So we were here. So
you may conclude your talk in 3-4 minutes.
Okay. So this is just a clustering because clustering play an important role. So small cluster means this social distancing, and the other thing is centralization, because in a graph theory the central node play an important role. Central node means this, suppose this is one city, this is the another city, this is the one city here, one city is here, and the second city is here, and third the third city. So by analyzing these graphs and this central nodes means if we disconnect these two cities, then the virus can not be spread from one city to other city. Or if we connect these two cities, and how weight we can give to some edges so that there is a very less spread of virus. So we can, so this is central node. Central node play an important role. Central node means this is the lockdown or some disconnection. Suppose we some take some barricade or police here so that the person cannot transfer from one city to another city. So we disconnect this. So this is the central node which play an important role in this. And next, just I would like to talk about the virus graph, right? Virus graph means because in the previous slides I talk about this the set which is constant cardinality. So I talk about the virus graph because in the virus graph their set is a variable set, because if we have a set of the infected person and some non-infected person set in a population, then infected person if they interact with some non-infected person, then the non-infected person will be infected. So the population of the infected person will increase, and the population of this non-infected will decrease. So the cardinality. So what is the variable set? A variable set uh, is a set in which the cardinality of the same set changes with respect to time or some other characteristics, right? For example, our population is a variable set because there is some birth every time and death every time, so the population changes with respect to time. So a variable graph, if the vertices or edges set in a graph is a variable set, then this is called a variable graph, and we represent this by this V graph. We denoted by this V graph. So first, this is a bipartite V graph. So a bipartite V graph, a bipartite graph, in a bipartite V graph, a variable graph, there is a vertex set in which there is two sets V1 and V2, and these are the disjoint set with different characteristics. Suppose this V1 set has some different characteristic and V2 set has some different characteristic, and an edge between V1 and V2 set. There is an edge between these two sets. Suppose this is one set, this is another set, and there is the edge between these two sets, but there is no edge on the same set. This is called the bipartite graph. But if the V1 and V2 are the variable set, then this is called a bipartite variable graph. Similarly, we can define the by n partite graph. In n partite graph, there are some n set, and this set of vertices is V is the this is the union of this V1 union V2 and this union Vn. So there is a edge between two sets which have the different characteristic, but no edges between the same set, right? So this is the n partite graph, right? So if you talk about there are four types of virus graph. In a first type of virus graph, this is a bipartite V graph in which the vertex set is I and n. V1 is I and V2 is n. I is the variable set of infected person, n is the variable set of vertices non-infected person, right? So if X is a person which interact with some person in the non-infected, suppose this is set of infected person and this is the non-infected, this is the I, this is the N, this is the vertices, there are some vertices of the infected persons, and non-infected person, these are the denoted by these nodes. If there is interaction between infected and non-infected, then this non-infected person will also be infected, then he will be transferred to this set I, right? So these person will be transferred to this set, and so if X belongs to I infected with Y person belongs to N, so there is an age between X and Y, so Y will be shifted to I, and so number of N will be N minus Y. And if X belongs to I is recovered by the treatment, suppose there is infected person here, and after the treatment, if he recover, then he will shift it, he will move to this set N, right? So these two are the variable set. So this is the one type of graph in which the vertex set are the variable sets, and there is a movement from the one set to the another set. And second type of graph is a tripartite graph in which the set of vertices is divided into three sets: the infected person, non-infected person, and the permanently infected person. Suppose we have these three sets, 1, 2, 3. This is the infected set, this is the non-infected person in a population, and there is some, suppose, permanently infected, right? Permanently infected means which cannot be recovered from the treatment. So if the nodes are here, suppose the infected person are here, non-infected person are here, so there will be the movement from here to here. If there is interaction between this infected or non-infected person, so then these person will be moved or shifted from non-infected to infected set. And suppose there is a person which cannot be recovered of the treatment, then he will go to this set, right? So there will be movement from here to here. This IP, this is the permanently, the IP means the permanently infected. So this is a IP is a non-decreasing variable set, and I and R and R, these are the variable set. So we can analyze using these type of graphs. And third type of the variable graph is also a tripartite graph in which we can take this graph infected person set, non-infected person, and IM means the person who gets some immunity, suppose by vaccination or by some antivirus development. So there is a set infected person set, there is a non-infected person set, and there is a set of person who has developed the immunity, right? So there is an infected person set, there is a nodes here, and there is non-infected persons, and there is a person here, right? These are the person who got the immunity, right? In non-infected. If there is a ages between these two sets, then this will be transferred to here, this will transfer to here, and suppose this person is recovered from the treatment, he will come to this set, and from this, suppose there is the person who have the immunity, that means he got some vaccination, because vaccine are coming very soon. So suppose they will move to this set, right? Initially this set, we can assume this set is empty set, or then after some times this set IM will also an increasing set. So these are the variable sets, right? And the fourth type of graph is a graph which is not tripartite. This is equal. There are the four partition in the set. So there are four in the vertex set. We can divide the vertex set into four disjoint sets: the infected person, the non-infected person, and the person who got the immunity, and the person who are permanently infected. So there will be the movement from this set to this set. This is the infected person set, this is the non-infected person set, this is the permanently infected, and this is the person who got the immunity, right? So this is the set. So if there is an interaction between these, this set to this set, so this was because the disjoint set, and there is an age between this, there is no age between any person of one set, right? So the person, if the infected, he will move to here. If a person got the vaccine, then he will move from here to here, and this permanently will move here from here to here. So there are four type of graphs. Though this coronavirus graph basically are from the type 1 and type 2. So this is some incitement about the graph theory and this spread of virus. We can make some models using these definition and using this kind of virus graph or variable graph. So I think it will help the student to understand the spreading of virus, and we can also make some policies by using these graph, analyzing these graphs for spreading of virus. So I just stop here.
Thank you very much, Joshi ji. Your ideas regarding the modeling of, I mean, any modeling, if we are able to model a pandemic through these graphs, then we can always think of modeling any mathematical model through these graphs. That's a pretty new idea. I don't know many people would be knowing it, or any, so researchers doing research in this direction may get benefited if they talk to Professor Anand Joshi ji. We can provide his email address to anybody who is willing to work in this direction. I invite any questions from the audience if they have. No. So in that case, I thank Anand Joshi ji for his fairly new talk. And next, I would invite another presenter, research paper presenter, Varun.
Yes, next candidate to present the paper is Amarnath Chatterjee. Amarnath Chatterjee, are you there? Amarnath Chatterjee. Okay, the next candidate is Mr. Jiten Singh. Jiten Singh, are you there?
Yes, sir.
Yeah, just share your screen and start your presentation.
Please allot some time to him.
Yeah, he is having around 8 to 10 minutes.
10 minutes.
Yeah, 7 to 8, 8 to 10 minutes.
Can you see my screen?
Yeah.
Okay, sir. Good morning to all professors. Am I audible?
Yeah. Yeah. Yeah.
Okay. Oh, my screen
Yeah.
is there. Okay. Okay. Good morning to all professors and colleagues. My paper title is Modeling and Analysis of the Effect of Household and Other Natural Discharges on the Spread of Bacteria-Dependent Infectious Disease. So here the idea is about the variable contact rate. So new thing is here is the variable contact rate. My collaborator is Dr. Sikha Singh and Professor J.V. Sukla from IIT Kanpur, retired professor from IIT Kanpur. So this is the abstract. In this research, the effect of the household and other natural discharges on the spread of bacteria-dependent infectious disease with contact rates as a function of non-immigrating population. Here the one new thing is non-immigrating population of the habitat. Non-immigrating population means those are not leaving the habitat due to some reason like the stability or job consideration. In the modeling process, we have chosen 4 dependent variables: the density of the susceptible, density of the infected, and the density of the bacteria population with cumulative density of the household and other natural discharges. Here, it is assumed that density of the bacteria follow logistic model, but also I include one more term: the density of the bacteria is depend on the number of infected as well as the household density of the natural discharges. The model is analyzed analytically as well as numerical simulation, and analysis shows the cumulative density of the household discharges increases, the disease spread of the disease is increases, that is bacteria dependent. And it is further shown that as the non-immigrating population of the habitat increases, the spread of infectious disease increases. So here something about the introduction. The infectious disease, we know that it is the communicable disease of the human habitat, and we all aware before that some of them are not knowing the what is the communicable disease. But in this pandemic, everyone know that what is endemic, what is the communicable disease like the coronavirus. Over the past 4 decades, we humans have tripled our global use of the natural resources, according to the recent report of the United Nations Environmental Programme. Globally, a large number of the people work with the household discharge collection, and exposure to the microorganism is considered to be the major health problem for the people handling the waste. It is well known due to the continuous emission of the household and other natural discharges. Various kinds of the communicable disease causing the bacteria grow and survive in the human habitat. The most of the communicable disease transmitted directly, indirectly, and environmentally. In most of the developing country, due to the lacking of sanitization facility, the rural area and the poor waste collection facility, various types of the disease causing bacteria such as Mycobacterium, tuberculosis, Vibrio cholerae are present in the habitat. So for all these, we are also aware about that the mathematical model plays important role as a tool which has been used to study which the infectious disease spread in the human habitat, predict the future and infectious disease, and the controlling the strategy of the infectious disease. Here, especially tuberculosis, an infectious disease caused by the Mycobacterium tuberculosis bacilli, remains one of the world's deadliest disease. Well, this report, I have cited this report, 2014 WHO report. And cholera is serious infectious disease in which the intense intestine become infected with Vibrio cholerae. The mathematical model for the transmission dynamics of the TB that examine the impact of the certain factor on TB cause detection and simulation analysis of the transmission dynamics of the cholera. In most of the classical model, interaction are assumed to be constant. But in the real situation, the density of the human population play an important role in the creating infectious contact for bacteria dependent infectious disease. So this is the new idea in my research. The density, the rate of interaction is assumed to be variable dependent. So in bacteria infection, the time of infection are longer, we know that, and the recovery is usually slower, okay, and the more preventable than the germs. Such infection does not guarantee protection from a reinfection with the same. So therefore, it is very important to study the effect of household and other natural discharges on the growth of bacteria, leading the spread of bacteria-dependent infectious disease. Most of the researchers using logistic model for the growth of bacteria, but the growth of the bacteria population is also depend on the various other factors, such as the cumulative density of the household and the other natural discharges. The spread of the infectious disease can be controlled by using the awareness and information program, but the disease remain endemic due to the immigration. The disease can also be controlled by the appropriate contact distance, which should be selected from the given disease to control associated infectious disease. So this appropriate contact distance, just like in the corona, we have certain advisory, we have to take 5 feet distance or 6 feet distance. So like that, if we create a appropriate contact distance, then the spread of the disease chance will be minimum. Okay. So in this paper, I have made some assumptions. The following assumptions are used to formulate the mathematical model. The contact rate increases as the density of the non-immigrating population of the habitat increases. This means if the number of people, certain number of people is not going outside from the habitat, so the habitat will be dense. And in the case of when the habitat will be dense, so the number of contact will be create more than the normal situation. The density of the bacterial population, the second assumption, the density of the bacterial population is also assumed to be governed by the logistic model with the intrinsic growth rate is the linear function of infected. So this is the assumption which make the this paper is new, and the cumulative density of the household and other natural discharges. The growth of the bacteria is also decreased with the rate which is proportional to the bacteria population. So bacteria also increase with the bacteria, and also the third thing, bacteria also increase with the help of the infected person, like in the case of the TB, and bacteria also increase with the help of the poor environmental condition, or like the garbage or cumulative density of the household and other natural discharges. Am I audible? Hello?
Yeah, you are
Yeah.
audible.
Okay, sorry. So in this paper, the contact rate between susceptible and infected is assumed to be. So here the contact rate is beta. Before that, most of the researchers use this beta n is the constant. But here I use this beta is the density dependent. So the density of the total population, and n naught is the non-immigrating population. Those are not going outside. Okay? And regarding this this contact rate, we published two papers in 2018 and 19. And the contact rate between susceptible and bacteria population also assumed to be density dependent, and which is the lambda minus lambda naught n minus n naught, which depend upon the density of the immigrating population of the habitat. In the view of our consideration, we have a mathematical model. These are the mass equations, like the differential equations, nonlinear differential equations, that is dx upon dt. This is the rate of change of susceptible. So the first term is A is the immigration, and the second term is A beta minus beta naught n minus n naught, that is the contact rate with the susceptible and infected. And the next term is lambda minus lambda naught is representing the interaction with the susceptible with bacteria. And as we know, the D is the natural death rate. So with the natural death rate, the people susceptible are decreasing with the D rate. And nu is represent the recovery rate, and those are ineffective. They are comes in this class with the rate nu. Also, the infected population change with the density of the infected population is changes, like beta minus beta naught. This term is also comes from the first class susceptible class to the infected class, and the XV that will increase the infectious contact, and nu minus alpha minus D. All these are the natural death rate and recovery rate and disease related death rate. And the new equation is here, the dB over dt, that is the increase in the bacteria. So here, see that theta s is the constant rate of increase, that is the intrinsic growth rate of the bacteria, and the phi is the coefficient of the interaction with by to the beta, that is the rate of increase of the bacteria. Overall, we can consider theta s plus phi y as a single term, that is the linear function of the y, that is also the non-negative. So this term is representing the growth of the bacteria with the linear function of non-negative linear function of the infected population. Also, the theta naught is the control variable of the bacteria, that is theta naught b square. This is due to the logistic growth, and theta 1 v c minus c naught, that represent the household discharges, natural household and other natural discharges. Okay, and the dc over dt, the household and other natural discharges, increase with the rate of q naught, that is the constant, and due to the mankind a minus dn. So a minus dn represent the population which help to increase in the cumulative density of the household discharges. And also the alpha naught is the rate to decrease the household discharges by the natural way. And here these are some conditions, initial conditions taken, and here by using n equal to x plus y, we can simplify these equation in the.
Sorry to interrupt you, Mr. Jitendra.
Yes, sir.
As we are running short on time, so
Okay.
can you just show us the important conclusions in just 2 to 3 minutes?
Okay, sir. Okay, thank you, sir.
Okay.
So here I use the equilibrium analysis, reproduction number, and region of attraction et al. And also the stability analysis. We found some theorems about the local and global stability. And these are the numerical simulation. These are the data is cited from some other research papers. And the conclusion is about the graphs. So this, you can see the beta, the second graph. The first is the phase analysis between n and y. And the second graph is for the beta. So it shows if beta is increases, that means the interaction rate is increases, then the disease will increases. And in the left lower corner, the beta naught graph shows if beta is increases, so the infected population is decreases. And because the beta naught is the coefficient of the non-immigrating population. Okay, so the immigration age increases, that means the infected population will increase. And the fourth graph is the lambda, that is the interaction with the bacteria to the human, that will increase the disease. And the fifth one, the upper corner graph shows the lambda naught increases, then the bacteria dependent diseases decreases. Also the theta 1 is increases, then the disease will increase. And with the phi and alpha 1 at the same scenario, if they increase, then disease will increase. Okay. So these are some references. Thank you.
Okay, thank you so much, Jitendra, for your presentation. It was a lovely presentation. Now I would like to call Ananya Devati. Ananya,
Yes,
are you
sir.
there?
Yes, sir.
Yeah, yeah. Yesterday you were not able to present the paper. You can try now.
Okay, sir.
Mr. Jitendra, you can just stop your presentation screen, I think.
Am I audible, sir?
Yeah. Your screen is clearly visible, so you can go ahead.
Okay, sir. So, good morning, good afternoon to all of you. My name is Ananya Divedi. I am working with under the guidance of Dr. Ram Keval, sir. I am from Madan Mohan Malviya University of Technology, Gorakhpur. So, my topic is mathematical analysis of a dengue model with various controls. So, these are the contents which I am discussed today. Firstly, objective introduction, problem assumption, formulation, and theorems based on assumption, optimal control analysis, and next conclusion.
Ananya, you have only 10 minutes, so just be specific on the results and conclusion section. Okay.
Okay. So my objective is basically propose a dengue model and find basic reproduction number, and by route criteria and Lucknow function discuss stability behavior. Next, we apply optimal control theory on the model and apply Rangakutta 4 method on this. So basically, dengue is a common viral disease in tropical regions. It is transmitted through Aedes mosquito, and the symptoms of dengue are appear in 3 to 14 days after an infective bite of mosquito. Most of the young and children, adults are affected through this virus. And on the observation of WHO, about 100 countries have become endemic, protecting half of the world population at with 50 to 100 million people infectious occurring annually. So there is no specific treatment available for dengue now. If human is recovered from dengue virus, it never affects human, and that human and never came and then given immunity for lifetime. So my assumption are here. I assume that the human population. So my total human population is NH, and the human population is divided into four parts. First, SH1, which is susceptible human at high risk, and next susceptible human at low risk. Next one, infected human, and next recovered human. So next compartment is total mosquito population, in which susceptible mosquito and infected mosquito. So this is by compartmental model. So here the human population has been divided into four parts. First, the susceptible class is divided already two parts. First, the high risk susceptible and low risk susceptible. So R and pi h is the recruitment rate of SH1, and 1 minus R pi h is the recruitment rate of SH2, where mu h is the death rate of both. Both are go with the infected human, and this is the rate of go to they are go with infected human is beta infected mosquito, it is beta alpha h sh1 plus theta sh2 into ih upon total nh plus m, where nh is the total human population and m is the number of source who's available as blood sources. Okay. Next, the infected human goes to the recovered human with Q rate. Now I'm applying control on susceptible human, which is U, and I am taking two type of control. First one is U is the education control, and second one U1, which is the treatment control. So basically U is give to the susceptible human and then the go to the recovered class, and U1 is give to the infected human which goes to then recovered class. And in a mosquito population, the SH1 SM is the susceptible mosquito with recruitment rate K, and delta is the death rate, and IM is the infected mosquito with death rate delta. So on the basis of this, we formulate a non-linear model, mathematical model. And with the use of this model, these conditions we obtain, and these are the biological significance of the parameter which I am using. So the system which I use above can also be written in this form to solve for the calculation. Next, we find the positivity and the boundedness of the system. So by Matlizar property, positivity and boundedness of the system. Next, we find the disease-free and endemic equilibrium point. So in early morning, Mitra sir already discussed what is disease-free and what is endemic. Disease-free means if virus present in the system or not, and endemic, the virus is confirmed that the system are present or not. So the disease-free equilibrium are this, and the endemic equilibrium are this. Next, we find the basic reproduction number by using next generation matrix method. Means the basic reproduction number. So means disease, how our model is how potential he has with disease or not, or they are specific for the treatment or not. So if R not less than 1, the disease-free equilibrium is locally asymptotically stable, and if R not is greater than 1, the disease is unstable. Next, some condition are occurred from the calculation, which shows that the endemic equilibrium in theorem number 3, which shows the endemic equilibrium is locally asymptotically stable or global or greater than if D22 is greater than, it is unstable. Next, the disease-free equilibrium is globally asymptotically, which is satisfies some conditions, and the endemic equilibrium, if it is satisfying this some condition. These are the find with the use of Lucknow function. Next, we discuss the optimal control analysis. So with the use of Pontigram's principle and using the two controls, we create an objective function on this form, and using some optimal control. And after using these controls, we get some effect on this. Here we see that when we apply the control on susceptible human, so with control and without control, there is a major difference between the graph. And one thing, the control is basically lie between 0 and 1. This graph has shown. Next, the infected human. When we apply the drug treatment on the infected human, so there is a difference between with control and without control. Next, this is the recovered human. Means when we not given their education campaigning and all these things, then they are much low, and after giving them, they are high. So this is our molecular. Here we assumed some parameters, and on the basis of this, we verify that in this figure, the global stability of endemic equilibrium. So basically, these are my work. Now, in this presentation, a dynamical model has been developed considering education and drug therapy control for humans. The model exhibits two equilibria, namely the disease-free and endemic. We see that the disease-free and endemic equilibrium is locally asymptotically stable if R naught is less than 1 and unstable if R naught is greater than 1. And further, we describe some possible conditions for which the system are stable. For the discussion of local and global stability, we use Routh-Hurwitz criteria and Lucknow function, which is a powerful technique for more and one-dimensional system. Next, we formulate optimal control and solving it by Ponticham's maximum principle. So these are my references which I am using. So thank you everyone for your attention.
Okay, thank you, Ananya. Okay, thank you, Ananya, for a lovely presentation. And now I would like to invite Mr. Haren. Haren, are you there? Harendra. Harendra, can you hear me?
Next.
There's some Haren, are you there? Okay, okay. There are some technical issues with the Haren's microphone, so I think we are just having all the members in the list. Is there anyone to present here? Because I don't think I can see the names online here. Somesh, Dr. Somesh, are you there? Dr. Ramajan? Dr. Ramajan? Dr. Pramod Kumar Rawat? Dr. Mahen Kumar Shukla? Are you there? So I think we are done with the presentations, and I would like to request Mr. Dr. Professor Pankaj Mathur sir to just say the few words to close up the session. Sir, are you there? Sir, your microphone is off, I think so.
Okay, thank you, Varun, for conducting this session of paper presentation. I hope everybody, I listened a few of the papers. All the presentations are very good, and we can see how much work is being done on COVID-19 and how much more is still awaited in this direction. So, mathematical modeling as the theme is of this webinar and technical session. It sounds, it was initially when we were talking about pandemic in mathematics, then there was some confusion, how can pandemic be related to mathematics? But with this webinar and the number of papers and the talks which were presented says all about how much mathematics has been involved in this pandemic. So, if there are no other presentations left, then we can move very quickly to our valedictory session of this webinar. Let me see if we have Professor Poonam Sharma ma'am and Professor Poonam Sharma ma'am is there. I see Professor R.K. Singh was there. Professor R.K. Singh was there a few times. Oh, he's there. He's there. He's there.
Yeah.
So I would request him to say a few words before uh, we are in our valedictory phase. So I would request Professor R.K. Singh Saab to say a few words. Although, okay, so he's there. Professor R.K. Singh Saab.
Hello, audible?
Yes, sir.
Yeah,
Audible?
yeah.
Yeah, very nice that Department of Mathematics and Bharat Ganit Prisad organized this 2 days webinar. It is first experiment, I think, in the department, and it was very successful. So far, I see that the presentation, and I'm surprised to see that people have worked on this pandemic with the help of mathematics, and they've obtained so many good results. So that shows the power of mathematics. Besides beauty, it is powerful, and that power comes from beauty because modeling is there, equations are there, theory is there, and all that applies to the problems of society and science. So this has been really a great session. I think I think this to be taken as a part of annual conference of Bharat Ganit Parisad. 2 days, and then one day we can hold somewhere else, sometime in January or February. So complete 3-day conference. So this can be taken. Well, I'm just suggesting because the technical part of the conference is the year, and I thank all the participants. Mostly, I find so many from so many places, and their interest in this technical session seems to be very encouraging. Mathematics, as you know, is a big thing. It is a beauty, it is a power, and it is complete in itself. It has its branches almost everywhere. You cannot do anything nowadays without mathematics. Without even literature, you cannot do without mathematics. Because in mathematics, objectivity is there. It is objective as well as subjective. When it is objective, it meets with science. Whatever your result is true here in Lucknow is also true in New York. It's objective. And it's subjective because you create it. Like poetry, poets, painters. Creation is there. So this combination of creation and objectivity, subjectivity and objectivity make it universal. Because for science you need a kind of faith, reason, and imagination. For science, lot of reasoning is there, and of course, lot of imagination. For poetry, you need faith. Of course, faith is required everywhere. Faith. I don't mean religion. Faith means that you can do it. That thing there. So faith and imagination with some reason, you can do poetry, painting, all those. But for mathematics, you got to have plenty of faith, plenty of reason, and plenty of imagination. They can create good mathematics. So mathematicians are a special species, and they have they make contact with everything in life. So I think this has been very good and successful session, and this 2-day program has been very good. I congratulate you, and I hope that if we arrange something of this type, even we can arrange our annual meeting in this way. So nice, and congratulate to all of you. Congratulations to all of you. Thank you.
You are muted.
Thank you very much, sir, for your nice praise of words and your recommendation and your suggestion that it will be considered as a part of technical session for our annual conference is really nice. Uh, Although we are planning to have a conference during 19th 20th February, and
Oh,
with the success of these 2 days, we are very excited, and hopefully we can do much better when we go for an online conference during 19th 20th February.
good.
So hope that all these participants would be there as well.
Hello, Pankaj sir. I would like to have one request.
Mhm.
Sir, Harind is there to present the paper. So can we give 10 minutes to Harind?
For
Harind is here to present the paper, sir. So can we?
paper,
Yeah, sir. Sir, can we give some 5 to 10
Madam,
minutes?
5 minutes. Okay, okay,
Okay.
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 5 minutes, 5 to 7
Harind,
minutes.
Harind, are you there? Harind?
Yes, sir. Yes, sir.
Yeah, yeah. Just start your presentation.
Hello, good afternoon, sir. My topic is if my topic is effectiveness of lockdown to crucial the spread of coronavirus.
The spread of
Coronavirus, a mathematical model.
spread of
Yes, yes, sir. Sorry, sir. In this paper, we have considered a mathematical model that deals with the effectiveness of the measures that may be helpful for reducing the spread of COVID-19 virus in the society. Here, we have illustrates the importance of the lockdown in controlling and maintaining the spread of COVID-19 virus. The impact of the virus on the susceptible population has been considered in the model. Also, we have taken into account that susceptible population which is able to reduce the possibility of getting infected from virus as they strong immunity and etc. My introduction is introduction. Introduction, a lot of mathematical models dealing with the different aspects of COVID-19 have come up recently. Most of them have considered the interaction of infected population with the stable population as a major uh, cause of infected individuals, whereas but the disease does not only spread through the direct contact between the susceptible to the infected individuals, whereas the infected individuals acts as a carriers of the virus and may spread the disease. As such, we have assumed that disease spread among the susceptible individuals through the transmission of virus that is presented not only the infected individuals but also in the environment. In the mathematical in the modeling model, we have considered the reason under consideration the total population NT at time t. The total population divided into three classes: susceptible class, infected population, and recovered population. As well as we also consider a VT, be the free virus presented in the infected persons at any time t. Here we have assumed that the disease COVID-19 spreads through transmission of virus to spread individuals by infected persons or through virus spread by the infected persons by coughing, sneezing, etc. at the place where he is visited. The growth rate of virus is assumed to the proportional of the number of infected individuals. In the model, ds by dt is equal to 1 minus a 1 minus mu, where mu is the rate at which the immigrant populations is in susceptible class becomes infected. So A is the immigrant population. So ds by dt, di by dt, dr by dt, or dv by dt. Whereas V is a virus. So change dV by dt is equal to AC is directly proportional to infected population, where the A is the number of immigrant pupil in the susceptible class, and mu is the rate at the immigrant population in the susceptible class becomes infected. Beta is the rate at which the persons in susceptible class moves to infected class. So B minus beta 1 minus MPS 1 plus AS, where A is the rate at which the infected persons move together with the susceptible persons without taking any preventive measures like putting a mask or maintaining the social distancing. In other words, we can say A is the measure of how much the lockdown has been followed by the public. The lower the value of A, higher is the effective of a lockdown at, and A is 0, imply the complete lockdown is strictly followed by the public. By solving the above model, we have used the fact n is equal to s plus I plus r. So reduce the following model in the model 2.2. For the mathematical study, we have the checking the positivity of the solution and boundness. Yes, basic reproduction number. We had find the basic reproduction number by using the next generation matrix. So basic reproduction number is the R naught is equal to AC1 beta 1 minus NP capital N naught 1 bracket 1 plus A N naught upon bracket C1 C2 minus C3 next bracket A plus delta alpha plus gamma. We have find three equilibrium point, disease free equilibrium point, and non-removal class equilibrium point. That means recovery is zero. The equilibrium point at which recovery is zero. And last equilibrium point is endemic equilibrium point. So we for that we had disease free equilibrium point. We have found the local stability, local asymptotic stability by using variation matrix, and global stability by using Lucknow function. uh, Same as we have non-removal class equilibrium points, we have using local stability for variational matrix and global stability for uh, uh, Lipnow function. And for endemic equilibrium point, we have calculated local stability for variational matrix, but global stability, we had found the geometrical approach method and autonomous convergence theorem techniques used for the global stability of the equilibrium endemic equilibrium point. For numerical simulation part, to, to check the feasibility of the effectiveness of the model, suppose we perform the numerical simulation, different values of the parameters involving have been estimated with the help of best fit, least square approximation, and the reproduction number have been calculated in each cases. Here is we have found constructed three cases. In case first, the reproduction number R naught is equal to 3.349 at 9, which means the spread of disease is, yes sir, the spread of disease is endemic and in happening the present situation. In case 2, NP is increased. NP is the like protection mask etc. NP is increased when the susceptible class becomes aware and takes some precautions by wearing protecting kit, wearing mask, washing hands, increasing immunity, and other parameters are kept fixed. The reproduction number decreases, but spread does not break, although it slows down. In case 3, A is increased. In case 3, A is decreased. That is the rate at which the infected individuals move together with susceptible individuals without maintaining social distancing or taking any preventive measures is decreased, and the value of other parameters same as in case 2. The reproduction number decreased and becomes less than 1. Starting the disease, spread of virus is decreased. Further, in case 4, When beta is transmission rate of the virus is increased and the value of other parameter kept same. In case 2, the reproduction number decreased considerably and virus decreased, spread of virus decreased. In case 5th, the value of age further decreased, the value of other parameters are same in the case 1st. The reproduction number decreased and becomes less than 1, which implies that the spread of virus gets breakdown in the and the infections get reduced. Now the comparative analysis of the real data conclusion. We have studied the total lockdown period in India. Lockdown has phases, 4 phases. First phase is 21 days, or second phase is 19 days, and third and fourth is 14 days and 14 days. So using real data, we have a best model fitting method to use by figures. For that, we have predicted at last. We had last predicted, assuming that the situation of the lockdown will be relaxed further, and more susceptible population will start to move freely. The possibility of these pupils coming in contact with the symptomatic and asymptomatic infected persons increases, and hence getting infected with COVID-19 virus also increases. With the suitable choice of parameters using the model 2.1, it is shown in figure 9. That's it. This is figure 9, that the spread of COVID-19 virus will come to an end in India by itself, but may take time approximately 2 years. As per the model, the peak value of the total number of infected population in India is approximately 1 cross 10 to power 7, and is expected to reach by the end of January 2021. If some medications of the vaccine is developed in the meantime, then the spread of maybe end up earlier. Thank you, sir.
Thank you, Haren, for a lovely presentation. Now, I would like to ask Pankaj Mathur sir to just wrap up the session.
Okay. Okay, Harim, thank you for your presentation. It was a joint paper with the. Okay, so I see Professor Manjuta ma'am here. Uh, I would like her to say a few words regarding uh, this webinar.
Hello, everybody. Am I audible?
Yeah, yeah.
Yes, ma'am.
Okay. So maybe I would like to thank all the speakers who presented seminars, webinars, and presented their work. It has been a good experience. But before I say anything, final word, I would like to seek opinion of others, like especially those who attended the webinars and paper presentation. Yes, any comment from anyone? Any suggestion? कोई नहीं सजेशन देने वाला है?
मैडम दिस इज पूनम शर्मा। मैडम इस समय जैसे स्थितियां हैं थी उसके हिसाब से बहुत अच्छी को हम लोगों का वेबिनार गया है और चारों ही लेक्चर्स बहुत अच्छे हुए और बहुत इंफॉर्मेटिव थे। मेरे ख्याल में जो लोग इस पर काम कर रहे हैं मॉडलिंग पे उनको बहुत अच्छा दिशा निर्देश मिला है इससे। तो हमें तो लग रहा है कि बहुत अच्छा गया है सेशन। पेपर रीडिंग थोड़ा कम हुआ है लेकिन फिर भी जो बच्चों ने प्रेजेंट किया बहुत अच्छा किया है प्रेजेंट। तो हम लोग को डायरेक्शन मिला है जैसे प्रोफेसर आर.के. सिंह साहब ने भी सजेस्ट किया है कि हो सकता है अब थोड़ा सा हम लोग और बेटर करें अपना इंफ्रास्ट्रक्चर। तो
That's what I also felt, you know.
तो कि एनुअल कॉन्फ्रेंस भी अच्छी होगी जी।
हाँ क्योंकि ये सर जी आप क्या कहेंगे सर?
Then first experience, good.
First experience is good, but the point is, yesterday I was present there, and somehow I felt at least one or two things which I felt that those who are in the audience, they cannot raise question unless and until they go to the podium, right? So that was missing. And second thing was that those who are presenting webinars, I mean, it was not visible properly. Those who are sitting maybe from distance. At least people of my age may not see that. So there has to be something other each side. I mean, you have to have some better infrastructure so that one can see, like at home we are watching our laptop and we can see better. So similar should be the situation there, if possible. That should be arranged. So better infrastructure definitely is required for time to come. The phase we are facing, I mean, I think we have to be on virtual most of the time, and so before I think this conference comes up, if we can have better infrastructure, that would be better.
Right.
This is my suggestion to Professor Poonam Sharma is that try to get better infrastructure, or maybe you can arrange somewhere else, wherever it's available. It doesn't have to stick to the department, if possible. And will it be? Is she hearing me? पूनम
Yes.
हाँ भाई ऐसा कह रही है कि कहीं दूसरी जगह भी हो जाए जहाँ अच्छा इंफ्रास्ट्रक्चर हो
बिल्कुल बिल्कुल हाँ जी
मैम हम लोग क्या का इंफ्रास्ट्रक्चर ही स्ट्रांग होगा. हम लोग यहीं पे करेंगे विद much better infrastructure. And this was the first experience at the department. So by the conference date, we will be equipped, much better equipped, and hopefully we will do the best we can.
It's no doubt. First experience has been really very good. There is no doubt about it. At least many people have heard the webinars and paper presentation, whether they were at home or present in the department. And second thing, which I suggested yesterday also, that it's better to have more frequent lectures by lectures or webinars on various topics, and maybe some workshop, etc. That would be nice under the banner of Bharat Ganit Parishad. That's what my suggestion is. And I am really thankful for all. It has been a really good experience, and I thank all the persons who attended and participated in this webinar session or technical session. Really, it has been a good experience. I thank all. सर आपको कहना चाहेंगे प्रोफेसर सिंह, आपने एक बोल दिया है क्या? प्रोफेसर सिंह का मैंने मिस किया. अच्छा.
Any other suggestions from the audience? Any other?
Yeah, that would be better.
Anybody who wants to say something? Dr. Shraddha Engle, ma'am. Are you there? Ma'am, are you there?
Yes, I'm here.
Ma'am.
Yeah. Yes, myself, Dr. Shraddha Engle from Ahmednagar, Maharashtra. And it's my pleasure to attend 2 days webinar hosted by Lucknow University and organized by Dr. Pankaj Mathur. So the session was conducted very nicely. All the speakers as well as audience, paper presentation, it was very nice. It gave me feeling that I have visited university once again. Thank you. Thanks a lot.
Good.
Thank you very much, ma'am. Thank you. Mathur. A.K. Mathur साहब. Papa है मैं. Are you there? Are you there?
I mean, from outside, I was thinking the only person from department.
Hello?
Yeah. We can listen you.
It's very nice to request me and given me an opportunity to say a few words.
It's very nice. I attended a few lectures. They were really very nice. And I quote Dr. Somesh Mathur's lecture, Dr. Arvind Sharma's lecture, Dr. Singh's talk, and Mrs. Manjula talk, and your head of the department, my students. I'm
जी
very much thankful to all of you who have given me an opportunity. I'm doing a paper, so I'll just speak about it, and I suggest and request you all to apply these operators on your theory, on your COVID-19 problem. Paper, this is the exact form of second moment of third degree Schoenberg spline operators. This paper is a very nice paper, and they have defined the operator in 1959. Schoenberg himself uh, discovered this operator, and this paper is from Camellia, Liliana Moldovan, and Radu Peltania. Very nice paper, and I'm sure that this pandemic problem can be very well explained and applied to these operators. The operators are the exact form of second moment of third degree Schoenberg spline operators. For second degree spline operators, they have been well dealt, but for third degree splines, they are not talked much. So I'll suggest all of you to go through and do some work in this lines. Thank you. And now I'll say a few words about the
नमस्कार सर,
concept.
आई थिंक बिफोर यू आपने बोला, एक्चुअली मुझे तो समझ में नहीं आ रहा था कि आपका नाम हम के माथुर की तरीके से जानते थे, केवल माथुर नहीं जानते थे सारी।
केवल कृष्ण माथुर जी।
अभी आवाज आपकी बिल्कुल बुलंद है।
अरे साहब, आप लोगों के साथ में रहे हैं ना, इसलिए बुलंद तो अब नहीं है, अब नहीं है बुलंद किसी जबान। थैंक यू, लेकिन थैंक यू फॉर द कमेंट्स। बहुत अच्छा लगा।
Thank you very much. Thank you very much, Papa. और ये nice और हम मैडम के सजेशंस पे जो मतलब पापा is right behind whatever research I am doing because he the time he spends in reading the paper line by line, word by word, that is awesome, and we cannot match it. So every time we write a paper, we always send to him, and he puts a comma, full stops, and all grammatical mistakes which we make, which we still make. He's always there to get it corrected, and a lot of suggestions on splines. I mean, he every day tells me like 10 problems in a paper, out of which if I'm able to do even one, then it gets, it's a huge work. I'm very much thankful and to him and for his rigorous efforts in getting me doing some research in the burning topics which are there. He's a reviewer of mathematical reviews, so he's getting papers every month, recent published papers of his direction every month, and so we are getting benefited with that. So thank you very much.
That is why it is why
पंकज ने एक्नॉलेज किया, ये बहुत अच्छा लड़का है, बहुत अच्छी जल्दी पकड़ता है चीज को। ये मैं इसके लिए कहूँगा। जो प्रॉब्लम्स मैंने अपने रिसर्च स्कॉलर्स को सबसे शुरू में जब ये रिसर्च कर रहे थे, जब जो प्रॉब्लम एक लड़की थी हमारी रेखा श्रीवास्तव, उसको हमने वो प्रॉब्लम दी थी, उससे नहीं निकली, तो वो इसने अपने आप करी थी उस वक्त में। तो ये बहुत, और इन्होंने दत्ता साहब के साथ में 6 रिसर्च पेपर्स किए हैं इंटरपोलेशन पे, स्प्लाइन पे, और जो कि शायद मेरे ख्याल से किसी ने नहीं किया होगा उनके साथ में। बहुत काम किया और अच्छा काम करता है, मेहनत बहुत करता है। जैसे ग्रेट क्वालिफिकेशन एंड आई
Okay,
विश
thank
हिम
you.
एवरी सक्सेस।
Thank you.
So, Pankaj, maybe you can ask some other persons who are present in the webinar, and then
Yeah,
you can.
anybody else who can say a few words regarding this webinar? Anyone else? Any research scholars? I can see a few names here.
Maybe Joshi, you can ask. Varun, you can ask.
Varun, can you? Jitendra?
Hello, sir. May I say something?
Yeah, sure. Jitendra, welcome.
Good afternoon to everyone. I am Jiten Singh, and that is students of Department of Mathematics, Lucknow University. I am now in Pondicherry, Arignaranna Government Art and Science College. Actually, since yesterday, I am listening this webinar and all lectures, and I am not a student of this modeling, but a little interest created, and I am thinking that in future I will do something in modeling field. And sir, one thing I want to suggest that the students who are very new for research area. Yesterday I saw a student that she is not presenting and showing mobile and so much disturbance. So for these types of new students, you arrange a practice session 1-2 slide earlier 1 or 2 days. Actually, they have so much hesitation and so much. I feel some nuisance type situation here in this webinar. That is not because so many professors and here and there throughout the world they are watching us. That's why. Because sometimes they don't know how to present. That is the technical problem, but it is very simple thing. But someone don't know. That's why. And because
Yeah,
thank
you're
you.
right. But Jitendra, what happens is, although what we did is Professor, one of our speakers was in a mock presentation a day before the conference started, and we were there for a mock presentation. Had anyone queried about a script, we would definitely do it. But nowadays, these things have become very common. Presenting a paper has become very, very common. I mean, we
Yes,
have been taking online classes. We are
yes.
taking. So I feel everyone should be equipped with it. But still, if anybody is feeling any sort of confusion, can always contact us, and we would try to help in whatever way we can.
Yeah, not faculty members, some students I saw only. Because the faculty members are taking online lecture daily. They know how to present. But that is for only some students. I saw that yesterday. Like
Yeah. There were a few. Yeah, your comment is correct. Maybe see next time
Yes.
when we do it. Anyone
Uh,
else?
Madhur sir, hello.
Yeah. Tata ji,
माधु
yes.
सर, थैंक्स माधु सर, आपने सर हमें मौका दिया सर अटेंड करने के लिए। इतना नाइस लेक्चर सर, हमने तो ज्यादा कई लेक्चर्स में शायद, लेकिन मैंने सर कोशिश की। और मैं सर बहुत ही जबरदस्त तरीके से सर आपने इस तरीके की सिचुएशन में सर, अपोजिट सिचुएशन में जो कि इस तरीके की शायद फैसिलिटीज अवेलेबल अभी पेंडेमिक सिचुएशन में सर, बहुत अच्छी तरीके से सर आपने सर कोऑर्डिनेट किया सर। मैं बहुत ही सर थैंक्स फॉर योर सर कि आपने मुझे इनवाइट किया। और मैं तो सर लखनऊ यूनिवर्सिटी में सर अभी अपने टीचर माथुर सर और आर.के. सिंह सर, मतलब इन्हीं लोगों के मार्गदर्शन में सर हम लोग कुछ कर पा रहे हैं आज। शायद कुछ थोड़ा सा 0.1% सब लोगों की जो सजेशंस हम लोगों को जो एक्सपीरियंसेस मिले, जो मैंने देखा आज की डेट में, बताइए सर, इतने मतलब अच्छी तरीके आज भी सर उतने ही एनर्जी के साथ जो है सर लोग बोल रहे हैं। वास्तव में हम लोगों को सर थोड़ा सा मिलता है सीखने को, शायद हम कुछ कर पा रहे हैं थोड़ा समय पर। थैंक यू माधुर सर, सभी लोगों को बहुत बहुत धन्यवाद सर।
म्यूटेड है आप।
Thank you so much, Patak sir.
जोसेफ
And
साहब, आप हैं क्या? विवेक जोसेफ जी, आर यू देयर? No. Okay. So, anybody else who wants to say something? Okay. In that case, I must thank all of you. Firstly, I must thank the speakers, Professor Somesh Mathurji, Professor, yeah, Jitendraji, are you willing to say something? You are unmuted. Please unmute yourself before saying anything.
Yes, sir. I just want to say thanks to organizers.
Okay, thank you. Thank you.
Everything is going well and very nicely. You present everything. So I just want to say thanks. Thank you very much. I will again be the part of this conference in the future.
Sure, sir.
Thank you, sir.
Okay, thank you, sir.
So I must thank the speakers first of all, Professor Sumesh Mathurji, Professor Rana D. Prasad ji, Professor Prashant Kumar Srivastav ji, Professor Arvind Mishra ji, for their first of all agreeing for this webinar, and then giving such a nice talk that the students and even my colleagues who are not working in this field got some interest in doing some research in mathematical modeling and especially on this pandemic. A lot of informations, economic informations, mathematical modeling information, and how mathematical models can be applied so as to get a estimate or how can the spread of the lockdown can be, how can the spread of virus during this pandemic period may be reduced. That was very much seen from the models presented. Professor Rana D. Prasad from Iowa State, he was there, and initially he was saying no to this presentation, but still he agreed for a paper, and he ensured that something he could speak on pandemic as well. Yeah.
Okay, that's nice. Actually,
So I'm
that's
thankful
what I
to.
had thought, in fact. I mean, it was away from the theme of the webinar.
Yeah,
Anyway,
it was initially a mathematical model on species.
yeah.
He's an expert for that, but anyhow, he said that he will sometime. So I'm thankful to all those. Then the thanks are due to all the the paper presenters. They were nice. I hope they will follow the comment of Jitendra regarding mobile presentation. They should avoid that, and next time when we meet them, they will be ready with their presentations on laptops so that those presentations are visible to everyone. Uh, then I must thank all the professors and all the executive members who have given me time to time suggestions, courage to do this webinar. I must thank Professor Manjul Gupta ma'am because for changing the title at the last moment, because the title which we were using was only webinar and not the technical sessions, and that was a technical fault in that in what we were doing, because we were going to have paper presentations, and during a webinar technically we are not allowed to do that. So thank you, ma'am, for a last minute suggestions. At that time, we were almost ready with our brochures and all. So all in all, it was a great effort, a great motivation, a great courage given to me that we were able to do that. Professor Poonam Sharma was always there, sitting all the day with me, looking out at the brochures and banners and preparing all the lists. And she was there to check out all the programs regarding the tea break and all. and I'm thankful to her for all the suggestions that she gave. And thanks are also due to all the members of the staff who were there to help me out. Dr. Anupma Rastogi was also there because she at the last moment she got her students to for Saraswati Vandana and the Deep Prajwalan she did it at the right time. The student to draw that Rangoli was really nice. It was a last minute effort. We are taking all these in our mind for our next project that is on during 19th 20th February 2021, and hope that all of you would be there to help me out again and with a very large number so that we can celebrate that as an event of COVID leaving here with the vaccine with us and with online and offline mode both. Thank you very much, all of you.
Pankaj, hello.
Yeah.
I like to say few words more.
Sure.
First of all, thanks to the organizers for having such a nice webinar and giving me an opportunity to say a few words. I'll add two words more that Manjul Gupta's guide, Dr. P.K. Kamthan was my student, and he was very nice to me and very nice student. I'll cite one incident for him. He offered a paper in MSc called electricity magnetism, and he got electricity magnetism was a paper in MSc final. He got 0.
Okay.
Then he got 0. Just listen. Then he asked Professor J.P. Jaiswal that how it can be. I have done all the questions correctly and I am getting 0. Then Dr. J.P. Jaiswal Sahab was in examination. He saw his copy and he found that all questions were correct. Then he got re-examined that and he got 125 out of 125.
Oh, great. This is surprising. I didn't know that.
I know that. I knew that. Because I also offered that electricity.
So you are my grand teacher, sir. Because you are his teacher. And so he was my teacher, so you are my grand teacher.
I know that. You were a student. That's why I wanted to say, very nice of you to listen to you and see you.
Thank you for your kind words. Okay.
Thank you. So I would request Manjul Gupta ma'am to end this webinar.
So it has really been a very good experience, and what I like, that since it was on one particular topic, so this trend I think we should also continue. We choose one particular topic of interest, whether it's current or old, and then we ask experts to give and deliver webinars. That would be really a nice thing. And I really thank all the speakers and for their suggestions. Those who were present and those who were not present. I mean, whatever suggestions we have got, I think I will request all of you to implement that for the coming annual conference. And I wish that not only you, others should also join the conference for which we are going to have on
February 19th, 20th February.
In virtual only, of course. So, but it has really been a very good experience, and I thank Pankaj Mathur and Poonam Sharma for giving me the chance to be there and other members as well. And I pay my regards to Professor Mathur and Professor Kishore, R.K. Singh, who have been, instrumental in giving me the chance for speaking here and there. That's all. But it has really been a very good experience. That's all. And if whatever help you need, one more suggestion which I would like to give. Let's see whatever books you have in your library, especially on mathematics and by other professors like Professor R.P. Agrawal and Professor Sunil Datta, etc. Put them on display. Are you listening to me, Professor Mathur? Professor Sharma?
Yeah, yeah, yeah.
So that would be better. Whatever you have, and those who are interested to buy, they can buy there itself. That would be better idea. Especially during conference, you may do that. This is my suggestion, and I thank all. And in fact, with these words, I will conclude the session. Okay? That's all. Thank
Thank
you
you
very
very
much.
much, ma'am. Thank you.
Thank you so much, ma'am. Thank you so much, Pankaj Mathur sir, Raj Kusur sir. And I would like to say to all the members that all your certificates will be delivered to you in email within 3 days. So be patient, and if you did not receive your certificates within 3 days, then only mail me personally. Okay. So just have patience for 3 days. We will be delivering your certificates via email. Thank you so much, Manjul Gupta ma'am, Raj Kishore sir, Pankaj Mathur sir, Jiten, and all the members for having this session. Thank you so much.
Thank you.
Thank you.
You are
Okay.
muted,
Bye,
sir.
everybody. All the best and bye.
Okay, thank you. Sir.
To all.
Now, all members can leave the session. Okay.
Okay, thank you. I'm
पापा
sorry.
मैं स्ट्रीम एंड कर रही हूँ सबसे पहले आप ही ने लीव कर डाला